we do inside partition. While these two pointers are far away from each other, first we check if the element at the left pointer is smaller than the pivot. Well, if the element at the left pointer is smaller than the pivot, which it is, you simply advance the left pointer forward. So this goes to 5. And then we go back to the next loop. Now this time, once again, we check if the element that the left pointer points to is smaller than the pivot. 5 is not smaller than 3, 5 is greater than 3. So if that is the case, then we check if the right pointer is greater than the pivot. Now, if the right pointer is greater than the pivot, that means this number is in its right position. It's greater than the pivot. So we move the right pointer back one space. Okay. So that's the operation we just did. Now, once again, we check, is the left pointer smaller than the pivot? No, it's not. Is the right pointer greater than the pivot? No, it's not. So that means these two numbers are out of place, right? We ideally would want this to be smaller than the pivot and this to be larger than the pivot. So we swap these two elements. So now 0 comes here and 5 comes here. Now, once again, we can check, is 0, the left pointer, smaller than the pivot? Yes. So move the left pointer forward. Then is the left pointer smaller than the pivot? No. 6 is now greater than 3. So we check, is the right pointer larger than the pivot? Yes. So we move the right pointer forward because 5 is still in its correct position. It's on the right edge and everything is greater than 3. So now once again we end up in this position that the left element is larger than the pivot. So we check the right element. The right element is smaller than the pivot. We want it to be larger. So we swap these two because these two are once again out of order. And now you can see that 1, 0, 2 are all smaller than the pivot and 6, 5, 11 are all larger than the pivot. So we do one final check. Is 2 smaller than the pivot? Yes. So we advance the left pointer and now both of the pointers are at the same position. So now we can tell at this point that here, from this point position onwards, all of these numbers are larger than the pivot. So we simply swap this element with the pivot. So there you go. So you end up with 1, 0, 2, 3, 5, 11 and 6. Okay, so that's the partition operation. So again, to understand it yourself, do it on pen and paper, write out this array, create the pivot, create the left pointer, right pointer, and keep creating copies of the array for each step of the loop. Okay, and that's how you understand these things. It's not that difficult. It's just, it involves 2 pointers, so it's a little tricky. Now, this is the code for partition, and I will let you follow this code. We'll go over this briefly, but by this point, since we are halfway into the course now, you should be able to read the code, and then there are also comments here, and understand what we have just discussed in plain English. Understand that in terms of code. Okay, so one exercise for you is to explain this visual approach in plain English step by step, and then the second exercise for you is to read the code and understand it, or maybe even try to write it from memory. So just take the English description and try to write the partition function from your memory. Not memorize the code itself, but convert the English text into code. Okay. So once again here, we have the nums, the numbers that need to be partitioned, the start and the end. And if end is none, we simply set end to the last index, which is len nums -1. Then we initialize the start and end pointers. So we initialize the left and right pointers. Remember, we want to use the end element. So this is the end element. So we want to use the end element as the pivot. So the left pointer is start and the right pointer is end -1. That's what we've set here. And then while the right pointer is greater than the left pointer, we increment the left pointer if the number at the left pointer is less or equal to the pivot. We decrement the right pointer if the number on the right pointer is greater than the pivot. Otherwise, the two of them are out of place and they can be swapped. So we swap them here. And finally, we place the pivot in place between the two parts. And that's it. That's exactly what's happening here. So let's see here. Let's see this partition. We are taking this list and we are calling partition on it. And 3 is the number that was used as the pivot. So now 3 ends up here in between. So you have 1, 0, 2 and 5, 11, 6. And the partition function returns the position of the pivot. So now you can see how it is used in quicksort. The partition function returns the position of the pivot, and then we call quicksort on the left partition before the pivot and on the right partition after the pivot. So now we can test out quicksort. Okay. And here's another exercise for you. Add print statements inside the partition function. So there are already some print statements. You can simply uncomment them. Uncomment the print statements to display the list, the left pointer and the right pointer at the beginning and end of every loop to study how partitioning works. And similarly, you can also add print statements inside the quicksort function to study how the recursive calls are going on. So study what we've done in merge and merge sort and add the same print statements in quick and quicksort and look at these recursive calls. Now, what you want is to have a completely clear and perfect idea of what your code is doing. You don't want to be lost about it. And that's why adding print statements and looking at small examples and making sure that it's working perfectly really helps. So let's look at quicksort in action. So here's an input and here's the expected output and here's the actual output, and they match. Great. And we can now evaluate all the test cases using the evaluate test cases function from Jovian. So we import from jovian.python DSA, evaluate test cases, and call evaluate test cases here. And you can see that it passes all the test cases. And not only that, you will also notice that it is marginally faster than merge sort for sorted lists. Sometimes you may not see that, but yeah, you can see here that you will see that in most cases, quicksort is marginally faster than merge sort for larger lists. And that's because it is not allocating new space. Okay. So now coming to the time complexity for quicksort. Now, assuming that we are able to have a good partition each time. So each time we are dividing the list into roughly equal halves, roughly equal parts. Like you start with a list of size n and you partition it into n by 2 and n by 2. So this is what the subproblem tree looks like. So you call quicksort with 2 lists of n by 2, n by 2. Then you call quicksort with 4 lists of size n by 2, n by 4, n by 4, and so on. Now, what is the activity that we're doing inside quicksort? In each quicksort, the core operation is partition, right? And that's what puts one element, the pivot element, into its right place. And then the element smaller than it to the left of it, the elements larger than it to the right of it. So the partition is where the actual work, the comparison and swapping happens. And how many comparisons do we perform in the partition? I would say that the number of comparisons is equal to the size of the actual list. And you can see that here. You can see that we are going on comparing numbers like this. We are comparing each number to the pivot. So each number gets compared to the pivot exactly once, roughly. And that means that there are a total of n comparisons if n is the size of the list. Okay. So we have n comparisons in partition. So partition performs n operations, or partition is an order n function. And what is the height of the tree? Once again, the height of the tree is log n, because to go from n to 1, it takes log n steps. You keep going n by 2, n by 4, n by 8, and so on. N by 2 to the power log n becomes n by n 1. And so the time complexity of quicksort is n log n if you're able to partition the array into roughly equal parts. And that is what happens on average. If you're picking random pivots each time, then you do end up with roughly equal parts. Maybe it's 75, 35, 75, 25, but that's still more or less in the same range. So the quicksort complexity is about n log n. And this is called the average case complexity. On the other hand, if you have a really bad partition, and a really bad partition is maybe you picked the smallest element as the pivot. Now, if you pick the smallest element as the pivot, then all the elements will go to the right of the pivot, and you will end up calling quicksort on a problem of size n-1. And then maybe once again, if you pick the smallest element as pivot, all the elements will go to the right of the pivot once again, and you will end up calling quicksort with a problem size of n-2. Now, this is an unbalanced tree or a skewed tree. And what happens in a skewed tree is that the height this time is the same as n. You can see n, n-1, n-2, n-3. So going up to 1, the height of the tree is n. But the amount of work involved in partitioning is the same, because you have to run through the entire list to partition the list, right? So that in this case, the time complexity is roughly n times n minus 1 by 2. So the time complexity is about order n square. And that's bad because that's as bad as bubble sort. But despite the quadratic worst case time complexity, quicksort is still preferred in many situations. Now it really depends on what kind of algorithm you need to use and what kind of memory constraints you have. Because quicksort's complexity is closer to n log n in practice, especially with a good strategy for picking a pivot. And a good strategy is picking a random pivot, but there's another one called picking median of medians. You can check that out as well. So that's n log n is the average time complexity of quicksort, and then n square is the worst case time complexity of quicksort. Now here's an exercise for you. Verify that quicksort requires order 1 additional space, which means that it does not really need to copy the array. We did create a copy because we did not want to affect our test cases, but we could have removed that line and quicksort would work just fine. So because you do not need to create a copy of the list or the array, it requires order 1 additional space, but because space complexity also includes often the size or the space required to store the input. So you can say that quicksort has the space complexity of order n. Okay, so if you get the question about space complexity, you may want to ask, are you talking about the additional space, or do you also want to include the input in the space complexity? So that's quicksort. And those are the two sorting algorithms we've looked at. So we've looked at bubble sort and we've looked at insertion sort, and then we optimized it using divide and conquer and got to merge sort, which is order n log n. But it also has a space complexity of, or the additional space requirement of order n, which can be avoided using quicksort, which uses order 1 additional space, but can have order n square complexity in the worst case time complexity. But with the right choice of a pivot, it is closer to n log n. So that's sorting. And you can see that Python is such an expressive language that all these sorting algorithms, which are often quite confusing to implement in C++ or Java, are actually pretty straightforward to implement in Python. All you need to do is follow the method, which is to state it first in plain English, have some test cases ready to test your function, and then write your code carefully, checking each line for errors, and create small functions wherever you need to. So try not to have too much logic in one function. A good rule of thumb is about 7 to 8 lines of code per function, no bigger than that. And that's not just for toy problems, but that's also, even as a software developer, something that you can try to follow. Just have 7-8 lines of code in any function. If you have more than that, try to split it into 2 functions. Okay, and this way it's very difficult for you to go wrong. So now let's return to our original problem statement and let's read it once again. You're working on a new feature on Jovian called top notebook of the week, or top notebooks of the week, and write a function to sort a list of notebooks in decreasing order of likes. Now keep in mind that up to millions of notebooks can be created every week. You want to build this for scale. So your function needs to be as efficient as possible. So first we need to sort objects this time and not just numbers. And second, we also want to sort them in the decreasing order of likes for each notebook. Okay. So all we need to do to use our merge sort or quick sort techniques that we've already discussed is to define a custom comparison function to compare 2 notebooks. Okay. But before we do that, let's create a class that can capture some basic information about notebooks. So here we have the class. So we're still following the method, so to speak, right? The step 1 was to come up with the input and the output format. So here is the input format. Our input format would be using this class. So we're creating a class notebook, which is title, username, and likes. So we create the class and that gets stored as properties, titles, username, and likes. And then we also have a string representation here. Then create some test cases. So now we are creating some test cases here. So we are creating some test cases NB0 to NB9, and let's put them all into a list. And you can see here that we now have a list of notebooks NB0 to NB9. And you can see that because we have a string representation, we can see that the first notebook is this AakashNS/PyTorch Basics, and it has 373 likes. And the second one is this, and it has 532 likes. And these are clearly out of order in terms of likes. Next, we'll define a custom comparison function for comparing the two notebooks. What it will do is it will return the strings lesser, equal, or greater to establish the order between the two objects. Okay, so it should return lesser when NB1 should come at a position or a index lesser than the position of NB2 in a sorted list. Okay, so in case of our problem, what that means is we want to sort things in the decreasing order of likes. So the first notebook should have the highest number of likes, and then maybe the second notebook should have the second highest number of likes, and the third notebook will have a lower number of likes, and so on. So if we have two notebooks, NB1 and NB2, and if NB1.likes is greater than NB2.likes, so then NB1 should come at a lesser index. Okay, so we will return lesser because it should come at a lower position in the sorted list. So we return lesser because we want a decreasing order. And if NB1.likes is equal to NB2.likes, then we return equal. And if NB1.likes is less than NB2.likes, so that means this is not, NB2 is the more like notebook, NB1 is the less like notebook, then NB1 should actually come at a greater position. So we will return greater. Okay. So this comparison function should return whether the first input to it should show up at a lesser position in the sorted list compared to the second input. Now in languages like C++ and Java, normally the convention is to return a negative number, 0, or positive number. But I find that Python allows you to return strings. Strings are first class citizens in Python, and it's a lot clearer when you are debugging things, when you face issues, to look at actual strings, and it's also easier to write code. So I prefer using strings, but you can also use numbers like negative, 0, or positive. That's totally up to you. So now here is an implementation of merge sort which accepts a custom comparison function. So let's see the merge sort function. So the merge sort function it takes a list of objects this time, not a list of numbers. And it also takes a compare function, which by default, we also provide a default comparison so that we can still use it with numbers. Now with numbers, and default assumption is if you want sorting in increasing order. So this is what the default sorting looks like for numbers. So that's pretty straightforward, but you can also pass a custom comparison function. So here we have the terminating condition. If the length is less than 2, then we simply return the list. Then we get the mid index, and then we call merge sort on the left half with the custom comparison function. We call merge sort on the right half with the custom comparison function. And we call merge with the custom comparison function. Now what happens inside merge? Inside merge, earlier, once again, we have these two halves, left and right, and then we have the custom comparison function. So we create pointers for the two of them, and then we also create the final result list, which is merged. And then we iterate over the left list and the right list. So while we are going through these, we compare the left element and the right element. So now we're calling compare. Now we're not doing the greater than less than comparison. Now we're calling compare. And if the element on the left is lesser or equal to the element on the right, then we append it to the result array and we increment the left counter. Otherwise, so lesser or equal means that the element on the left, the first element on the left, should show up at a lower position in the final sorted list. So that's why we append it first. Otherwise we append the right element, and we increment the right pointer. And finally we attach any remaining elements here. So this is something that you can review, something we've covered in a lot of detail. So now let's call merge sort on our notebooks, and let's check if the notebooks are sorted by likes. And indeed they are. You can see that at position 0, you have the notebook with the highest number of likes, and then you have the next one and the next one, and so on. Now, since we have written a generic merge sort function that works with any compare function, we can now very quickly use it to sort the notebooks by title as well. Or if we had maybe the number of views per notebook, or the number of versions in each notebook, or the number of comments on each notebook, we could do that sorting as well. So we could even use a hybrid of those. So here, the example we're taking is comparing by titles. So here we have NB1 and NB2, and simple comparison strings can also be compared using the comparison operator. So if NB1.title is less than NB2.title, then we return lesser. Otherwise we return equal or greater. And with this, we should be able to sort them in the ascending order of titles. You can see AN, CI, CI, FE, LI, LO, PY, PY, okay, PYTH, PYTH, PYTO, PyTorch. Okay, so this is now sorted in the order of titles. An exercise for you is to sort in the order of username/title, which means you first compare the username, and if the usernames are equal, then compare the titles. So you can probably write another comparison function, compare username and titles, and use that to do that 2-level comparison and use that for sorting. Okay. Now another exercise for you going forward is to implement and test the generic versions of bubble sort, insertion sort, and quick sort using these empty cells that are given here, right? So now at this point in the course, you should start writing code. You should be writing, maybe solving one problem every day to really practice the concepts and internalize them. And while you're doing that, you can also, any problem that you work on, any notebook that you create, you can save it to jovian.commit. And I'll show you also how to create new notebooks. So one way to create new notebooks is to go to jovian.ai, click the new button and click blank notebook. And you can give it a title. Let's say you are doing quick sort generic, and you can set a privacy and create a notebook, and that creates a notebook for you. And then you can click the run button and run it. So that's one way to do it. Another way you can do it is we've given you a problem solving template. So if you come back to the lesson page, you will find a problem solving template here. Now you can click on the problem solving template and click duplicate to create a copy of this notebook in your profile. So let's do that. And now this is on your profile. So you can now click run and then run it on Binder, or you can even run it locally on your computer and make some changes to it and come back and run jovian.commit, and you will end up with a link that you can share. So now you can now go on Twitter and you can just share this link. So write out a tweet and tag us, and also use the hashtag 60 days of Python. Okay, and maybe say this is your quick sort algorithm for generic objects, and tweet it out. And we will retweet your tweet. So we want to support everybody who's taking part in this course. On the course page, you will find a link to the course community forum, which is where you can go and ask questions, where if you have questions about any of these, and you can even discuss some of the ideas that are discussed here, some of the exercises that are shared. So you can go into lesson 3, for instance, and create a new topic. Maybe you want to talk about the generic implementation of quicksort. So maybe you can create a new topic and post a query there. If you're not able to make it work, post your notebook there and ask a question, have a discussion. And if you are helping other people out, if you're answering other people's questions and you've written some really great posts, there are links to some more problems that have been shared here. So you can check out these links. On each of these links, you can try out problems, you can make submissions, you can solve these problems. Some of these are interview questions as well. You can check if your results are correct. And you can use this problem solving template as a starting point, as we've just shared. So there is a starter notebook with each assignment. And in the assignment, all you need to do is run the notebook. So you can run it on Binder, for instance. And then there is a question mark in a bunch of places. You will find like question marks here in the text, and you will find question marks here in the code. So you simply need to put in your code, your answers into the question marks. So replace that with your code. You can see here, there are some question marks here. So you replace that, and step by step, there are instructions to guide you. There are comments to guide you. So step by step, you can solve it. And then finally, you can also make a submission. So right at the very end, when you run the code, you will also be able to submit directly. And when you make a submission, then the assignment will get automated will get evaluated in an automated fashion instantly, and you will get a pass or a fail grade. Now, if you get a pass grade, that's great. But if you get a fail grade, then you will also get some comments about what went wrong in your solution. So you can use those comments to fix the issues. So it's a great way to get quick feedback and keep fixing your issues, and especially watch out for edge cases. So that's assignment 1. And then assignment 2 is called hash tables and Python dictionaries. A very interesting assignment where you are going to implement hash tables which power Python dictionaries from scratch in Python, and you will also replicate the interface of Python dictionaries. So do check it out. A very interesting assignment. Again, very similar format. You will find question marks in certain places. You need to replace them with appropriate values, expressions, or statements. And in this way, by working through each of these step by step, you can see here, by working through each of these, you will implement hash functions and hash tables, which again are very commonly asked in interviews as well. So this is an important assignment from an interview preparation or coding assessment preparation as well. And it also teaches you a lot of really good practices in Python programming in particular. So do check out assignment 2 as well, and we will send you an email as soon as assignment 3 is ready, but you can check back in a couple of days and you should see it on the same page, pythondsa.com. So what do you do next? Review the lecture video and execute the Jupyter notebook. Use the interactive nature of Jupyter to experiment with the code. Complete the assignment and attempt the optional questions as well. So each assignment has some required questions, and you can make a submission as soon as you're done with the required questions. But there are some optional questions which are slightly harder, but I highly recommend doing that because they will improve your understanding, give you more practice, help you internalize the concepts better. And then participate in forum discussions and join or start a study group. So this is a great way to learn. Get together with some friends, maybe watch the lecture together over a Zoom call, pause the video, have discussions wherever you have doubts. Discussion is a great way to solve the specific doubts that you may have. And it will also help you to articulate your understanding better, because when you explain to others, you also answer a lot of your own questions. So please do that. This is data structures and algorithms in Python. Thank you and good day or good night. Hello and welcome to Data Structures and Algorithms in Python. This is a live online certification course being organized by Jovian. Today we are on lesson 4, recursion, memoization and dynamic programming. My name is Akash and I'm your instructor. You can find me on Twitter on @AkashNS. If you follow along with this course and complete the weekly assignments, you can also earn a certificate of accomplishment, which you can add to your LinkedIn profile, and you will find hosted on your Jovian profile as well. So let's get started. Now to the Data Structures and Algorithms course. This is pythondsa.com is the course website, and on the course website you will be able to find all the information about the course. So you can view the previous lessons, lessons 1, 2 and 3, and you can also view the previous assignments, assignments 1 and 2. Today we are on lesson 4, so let's open up lesson 4. The topic is recursion and dynamic programming. Now you can find a recording of the lesson here, and you can also watch a version in Hindi if you would prefer that. In this lecture, we will cover recursion, memoization, and dynamic programming by looking at two common problems in dynamic programming, the longest common subsequence problem and then the knapsack problem. And we'll do this by coding these problems live using the problem solving template that we have been using in one way or another since lesson 1. So let's open up the problem solving template. This is a template that you can use to solve any coding problem, and we will illustrate this by solving two problems using this template today. So the first thing we need to do is to run this template. You can see that there is some explanation and then there is some code here as well. Now to run this code, you have two options. You can run it using free online resources, or you can run it on your computer. The simplest way to run it is click the run button here and select run on Binder. And with just one click, this will set up a machine on the cloud for you, start a Jupyter Notebook server, and you will be able to then execute the code and modify the notebook and save a version of it to your own profile so that you can continue working on it. So there we have it. Now we have a running Jupyter Hub server. I'm just going to zoom in here a bit so that you can see things clearly. Okay, so this is the problem solving template, and I said we're working on 2 problems. So I have some problem statements listed out here. You can see the first problem, longest common subsequence, is listed here. And this is a part of the lesson notebook, lesson page as well. So you will find link to this problem statement on the lesson page too. So let's first modify the title of this notebook, problem solving template. Let's change this title to dynamic programming, longest common subsequence. Let's get rid of this. I don't think we need this. Then I'm going to keep the section on how to run your code so that if I share this notebook with somebody else, they have a way to run it. And then before we start the assignment or the problem, let's just save this to our own profile. So I'm just going to give it a name. Longest common subsequence. This is an appropriate name for it. So I'm going to give this a project name, install the Jovian Python library, and just run jovian.commit. Now what this will do is we started out with a template and now we're editing the template. By running jovian.commit, we've saved a copy of the template to our own profile. You can see this is the link where you will be able to access this notebook and you can run it and continue your work if this Jupyter Notebook shuts down, if you want to continue tomorrow, for instance. Okay, so now let's look at the problem statement. Now I'll just copy over the problem statement here as well so that we can see it directly within the notebook. There we have it. Now you can paste the problem statement, and if you are getting this problem statement from some other source, then it's always a good idea to include the link to the original source as well. Okay, now we have a problem statement in front of us. So the question is, write a function to find the length of the longest common subsequence. So that's a new term. We'll unpack that between 2 sequences. Now let's first learn what we mean by a sequence. Now a sequence is a group of items with a deterministic ordering. For instance, a list, a tuple, a range, or even a string. These are some common sequence types in Python. So here I have the string serendipitous. This is a group of items, and this also contains an order. You can see that E comes after S and R comes after E and so on. So this is a sequence. A list would also be a sequence, so that would be a list of numbers. So that's a sequence. Then we're looking at subsequence. What is a subsequence? Now a subsequence is a sequence that is obtained by deleting or removing 0 or more elements from another sequence. For instance, if you look at serendipitous, and if we remove the characters S, R, E, N, I, O, U, S, then you will be left with EDPT. So EDPT is a subsequence of serendipitous. Now, 2 things to note here. EDPT does not have to occur continuously. So these elements can occur anywhere within a sequence, but the order should be the same. So EDPT occur in this particular order here, and EDPT should occur in the same order here. So D should occur after E, and P should occur after D, and T should occur after P. So those are the 2 requirements for EDPT to be a subsequence of serendipitous. And visually speaking, what we can see is if you take a sequence and then you draw boxes around some of these characters or some of these elements of the sequence, and if you just take the elements in the boxes, then in the same order, then you end up with a subsequence. So now we understand what a sequence is and what a subsequence is. And once again, if this question is asked in an interview and you're not sure what you mean by a longest common subsequence, then or even what a sequence is, then you should ask the interviewer, what do you mean by a subsequence, or what do you mean by a sequence? And they'll be more than happy to tell you. It's very important to communicate whatever you're thinking, whatever questions you have. Contrary to what you might think, asking questions is actually a good thing. The more questions you ask, the more it is appreciated. Okay, so now we've talked about a sequence and a subsequence. Now, what's a common subsequence? So look at these two strings, serendipitous and precipitation. Now, if we pick just these elements that are in the boxes, REI, PITO. Now you can see that REI, PITO is a subsequence of serendipitous, and REI, PITO is also a subsequence of precipitation. So a subsequence which is common, which is a subsequence of both sequences, is called a common subsequence. So REI, PITO is a common subsequence between serendipitous and precipitation. Now you can have many common subsequences. For instance, we could just look at RE and RE here, and RE would be a common subsequence too. Or you could just look at IT and IT, and that would be a common subsequence as well. Or we've not picked N here, but you could also pick REN and REN, and that would also be a common subsequence between the two. Now, the longest common subsequence, as the name suggests, is the subsequence which between the common subsequence between the two sequences which has the maximum possible length. And you can verify this. You can try different subsequences and see that REI, PITO is the longest common subsequence between these two strings, these two sequences. And its length is 7. 1, 2, 3, 4, 5, 6, 7. So you have to write a function to find the length of the longest common subsequence between two sequences. So that's the question. And this is a visual example that tells you the answer. Okay. So now that we have the question, we've understood the question, we can start applying the method that we have been learning throughout. So this is the systematic strategy that we will apply, and nothing about this method has changed since the first lesson, even though we've covered a whole variety of topics like binary search and binary search trees, and then sorting algorithms and divide and conquer. This method has remained the same. The first step is to state the problem clearly and identify the input and output formats. Then the second step is to come up with some example inputs and outputs, and these will be used to test our solution. So we should try and cover all the edge cases, and that will help us write code that is correct, anticipating all the errors that we might face. Then we come up with a correct solution to the problem and state it in plain English. Very important for you to state the problem in plain English before you start coding, so that you communicate your ideas and you also make it clear once you express yourself. Then you implement the solution and test it using example inputs. And you fix bugs if you find any of them. And you will be able to find bugs if you have written good test cases. Then you analyze the algorithm's complexity and identify inefficiencies if you have any. And most likely the first solution that you come up with, it doesn't have to be optimal, it just has to be correct. So there will be some inefficiency, but it's important to go through that process of first finding a brute force solution and then finding the inefficiency. And then apply the right technique to overcome the inefficiency and repeat steps 2, 3 to 6. So you identify what's the right technique. And in this case, we will learn a couple of techniques called memoization and dynamic programming. And then we go back and state the correct solution again. Then we implement the solution and test it, and then we analyze it again. And if there's further scope for improvement, we do that. Otherwise, we say that we've arrived at a optimal or good enough, optimal enough solution. Okay. I hope by this point, you've started to memorize this process, and that's why we keep repeating it over and over, that it should become second nature every time you see a problem. So the first thing is to state the problem clearly and to identify the input and output formats. Now, the problem is already stated clearly enough, but let's just state it slightly more clearly. So let's say we are given, and just write it in your own words, that's more important, whatever is clear to you. So we are given two sequences, and we need to find the length of the longest common subsequence between them. Simple enough. Then we have two inputs. Now we decide the input and output formats. So we have sequence 1, a sequence, example, serendipitous. Sequence 2, another sequence, example, precipitation. Great. And these are the only two inputs that we require, and the output would be the length of the longest common subsequence. Let's just abbreviate that as LCS. Which in this case is 7. And we know what that subsequence looks like. We've just seen it above. So now based on this, we can now create, and you can see the problem is now created. And before I talk about the next thing, if you double click on a text cell, you can start editing it. And here we are using a language called Markdown. So you can see this creates a block quote, this creates a bold font, and this creates a code-like font. So let's see here, and the way to go back into the display mode is to press Shift plus Enter. So now you can see here that now we have the problem, we have the block quote, and then we have all the styling. So Markdown is a really useful and easy to learn language for formatting your text, especially in Jupyter Notebooks. So do learn it. But now based on this, we can now create a signature of our function. So our function len LCS will accept a sequence 1 and sequence 2, and it will return something. Okay, so that's the basic signature of our function. And even though it's not doing much, just establishing what the arguments are is the first step towards solving a problem. And let's just save our work. From time to time, it's very important to keep saving your work on Jovian, because this is running on a free online service. So this will shut down after some minutes of inactivity. So just run jovian.commit, and that will save the notebook to your profile, and you can rerun it. Okay, so now the next step is to come up with some example inputs and outputs. And here we need to try and cover all the edge cases. So I have written out a few test cases here already. Now the most common case is a general case of a string, like we had serendipitous and precipitation. That's a common case. There is one of them, both of them have some common elements, and there's a common subsequence of length 7. But we may also want to test out another type of data. And this is one of the nice things about Python, where you can write functions that operate not just on a particular class and its subclasses, but on any kind of data as long as it satisfies certain criteria. For instance, strings and lists both allow indexing into them and picking out the ith element or the nth element from the sequence. So they're both sequences. So our function should be able to work with both strings and with lists. Then here is another case where we have two sequences and they have no common subsequence. Our function should not throw an error here. It should gracefully return the number 0, because the empty sequence is a subsequence of every other sequence. Does that make sense? Think about it. So in that case, if there's no common subsequence, then the empty sequence is the common subsequence. So the answer is 0. Then here's one other extreme case where one is a subsequence of the other. Here's another case where one sequence is empty. Here's another case where both sequences are empty. So all of these are important. Otherwise, you might miss out certain special cases and you will face an error when you code your solution. Finally, you can also have this case where you have multiple subsequences with the same length. For instance, if you have A, B, C, D, E, F and B, A, D, C, F, E, then A, C, E is one long subsequence of length 3, and that's the longest you can verify. And B, D, F is another subsequence which is common to the two and also has the same length. So those are some test cases. Now let's copy over these test cases here. In an interview or a coding assessment, what you might want to do is just write these as comments if you have just a single coding screen, and try to list at least 4 or 5, but go as far as you can, because this will also help you streamline your own solution. And it's always something that is appreciated by interviewers. Let's do that. Let's copy over these test cases here. And you can think of more. So if you have some more ideas of things you should test, come up with them. There's no right number of tests. Whatever it takes for you to feel confident is what you need to do. Okay. So now what we've done is we've taken these test cases and converted them into dictionaries. So you can see here we have this first sequence 1. And remember, that's why we've written out here the names of the inputs and the signature of the function. Now we can create test cases as dictionaries so that we can test them all easily all at once. So we have the sequence 1 and sequence 2 in the input sub dictionary inside the main test case dictionary. And then we have the output, which is the output of the function, which should be 7. And this you can verify. So this is a general case. Then we have another case. In this case, we have 2 sequences. These are both lists of numbers. And in this case, the output that we expect is 5. And we have another general case, longest and stone. In this case, you can verify that O and E is the common subsequence. It has the output 3. Then here we have 2 sequences which do not have any common elements. All these come from the left half of the keyboard. All these come from the right half of the keyboard. So that was a quick way to generate these 2 sequences. Then here we have dense and condensed. And you can see that dense is actually a piece inside condensed. So this is a special case where dense is a continuous substring of the string. But even if we had DESE, that would still be a subsequence because DESE occur in this order. So that's one example. And in this case, the sequence 1 is itself the longest common subsequence and it has length 5. Then we have this case where one of the sequences is empty. And you can see in that case, the output should be 0. And both sequences are empty. And here is the case where you can have multiple longest common subsequences. And even in this case, your function should be able to figure out the answer correctly. So let's take this and let us copy over these test cases here. So we have T0 to T7. So that's 8 test cases. And you can add more test cases here. Please feel free. Coming up with good test cases is a skill that you should develop. And what we'll do is we'll also put all these test cases into this function called LCS, or longest common subsequent tests, so that we have all of them easily available for testing at once. Okay. Now next step is to come up with a correct solution for the problem. Now we've seen the problem, we have identified some scenarios. Now we need to come up with a simple correct solution and state it in plain English. It doesn't have to be efficient. It just has to be correct. So here's one idea. Here you can see we have a couple of sequences. Let's create 2 counters, IDX1 and IDX2, both starting at 0. So IDX1 will be a pointer which will start tracking elements in the first sequence, and IDX2 will be a pointer which will start tracking elements in the second sequence. And what we'll do is we will write a recursive function. So we'll write a recursive function which will compute the LCS of sequence 1 from IDX1 to the end, and sequence 2 from IDX2 to the end. So what does that mean? Let's say IDX1 has the value 3 and IDX2 has the value 1. So you can see 0, 1, 2, 3. So sequence 1, IDX1 onwards is LOGY, and sequence 2, IDX2 onwards is LCHMEMY. So we are looking at this portion of the problem and this portion of the problem, and our recursive function, when invoked with IDX1 and IDX2, should return the length of the longest common subsequence between these 2 portions, so LOGY and LCHEMY. Now why are we doing this? We need this longest common subsequence for the entire string, don't we? Now here's the logic why we're writing this recursive function which can theoretically compute this subsequence from any position onwards. So here's how we do this. if sequence 1 of IDX1, so if IDX1 was pointing to L and IDX2 was pointing to L here as well, if sequence 1 of IDX1 and sequence 2 of IDX2 are equal, then this character L belongs to the LCS of this portion and this portion. Okay, why? Think about it. It makes sense because these elements are equal. So if you pick the longest common subsequence of this and you pick the longest common subsequence of the remaining, then you can always add L to that subsequence, and that will make the subsequence longer, right? And that way it follows that L will always occur in the longest common subsequence between LOGY and LCHEMY. Okay. So we know now that this will occur, L will occur in the longest common subsequence. Further, the length of this longest common subsequence will be the length of the longest common subsequence between OGY and CHEMY plus 1. Okay. And now you can see why recursion is required, because what we can now do is we can say that if sequence 1 of IDX1 and sequence 2 of IDX2 are equal, then we simply call the recursive function on sequence 1 of IDX1 plus 1, so OGY, and sequence 2 of IDX2 plus 1, CHEMY, and assume that recursion will give us the solution there, and simply add 1 to it because this is equal. Okay, so that's one case. If sequence 1 of IDX1 and sequence 1 of IDX2 are equal, great. But if they're not equal, right? So in this case, for instance, you can see that if IDX1 and IDX2 are both 0, so IDX1 points to A and IDX2 points to B. So if they are not equal, then one of the two things should hold. Either A does not occur in the longest common subsequence between the two strings, or B does not occur in the longest common subsequence between the two strings. Now we don't know which one, but that's the power of recursion, that we can just try both. So we can simply ignore A and we can get the longest common subsequence between BSENT and BEST and check its length. And then we can simply ignore B and we can get the longest common subsequence between ABSENT and EST and check the length. Now whichever is longer in length, that becomes the solution for the two strings. Okay. So this is what it looks like. We start out with analogy and alchemy. We compare A and A. These two are equal. So we know that the longest common subsequence is 1. The length is 1 plus LCS of analogy and alchemy. Okay. Now we compare N and L, and now we see that they are not equal. So either N does not come in the longest common subsequence or L does not come in the longest common subsequence. So we try both. We remove N. Here you see ALOGY, and we remove L. Here we see CHEMY. Now once again, A and L are unequal. So either A does not occur in the LCS of these two strings, or L does not occur in the LCS of these two strings. So if A doesn't occur in the LCS, we can remove A and try again. If L does not occur in the LCS, we can remove L and try again. And here once again we get a match. So in this case, we know that L occurs in the longest common subsequence of these two elements. So now we can get the LCS of OGY and CHEMY. Okay. And then, as these recursive calls complete, you can see that this entire tree pans out. You can see that each time you either get one child or you get two children. And if you go all the way down and then you go back up and simply count the number of matches for each path, you will keep taking the maximum. So here you get back an answer. Let's say you get back an answer of size 2. Here you get back an answer of size 1. So the answer for this is simply the maximum of 2 and 1, which is 2. And then the answer for this is simply the maximum of 2 and let's say if this is 3, then 3. And the answer for this is simply 1 plus 3, 4. Okay. So this is the way that we will build up the solution. So we've now looked at the recursive solution expressed in text, and we've looked at the recursive solution expressed as a tree. Now it's possible that it still may not make sense to you how exactly this is working, and that is where you should start trying to create this tree yourself. So pick up a pen and paper and then start drawing on pen and paper. Take an example and try to read each step here and try to work it out like a computer. Okay, and just thinking about it that way will help you understand this algorithm. Now, one last thing is that if either of the sequence 1 from IDX onwards or sequence 2 from IDX onwards is empty, which means the index has reached the end point in after doing some recursion, then their LCS is empty, so the length is 0. Okay, so that is the recursive solution here. I will just copy over this recursive solution too, along with the entire tree. Now, obviously, in an interview, you do not need to write all of this in a lot of detail, or you do not need to. So it helps to show a diagram sometimes, but you don't really need to do all of this. All you need to do is express yourself clearly that we will create 2 counters, and the condition to check is whether these 2 elements at those counter positions are equal. What do we do if they are equal? What do we do if they are unequal? And why are we using recursion here? So we are using recursion because we can reuse some of the sub problems to compute the final problem. Okay, and understanding recursion is really important for solving data structures and algorithms problems, because it's like a superpower. Pretty much every problem that you see, one way or another, does boil down to recursion in one way. Okay, so now let's save our work once again. And now we're ready to implement the solution. So we have the recursive solution in front of us. And if you remember the 4 steps, let's go ahead and implement it. So we see, let's just call it LCS recursive. And this will accept a sequence 1 and a sequence 2. And let's also initialize IDX1 and IDX2, because we will be calling this function recursively. So we'll simply use these 2 counters, IDX1 and IDX2, and set them to 0. Now the first thing we need is if IDX1 is equal to the length of sequence 1, or IDX2 is equal to the length of sequence 2, then we return 0. Again, this is a common thing that happens, that the base case or the end scenario is something when you're describing the algorithm, you will describe at the very end. As you're drawing the tree, you will notice what the end scenario is. But when you're coding the algorithm, the end scenario or the base case comes at the very top, because otherwise we'll try and access IDX1 from sequence 1 and that will throw an error. So that's why you need to handle the base case at the very beginning. Okay, next, moving ahead, if sequence 1 of IDX1 equals sequence 2 of IDX2, great, we found a match. So we simply return 1 plus. Now we can call LCS recursive on sequence 1, sequence 2, and we increment IDX1 by 1. And we also increment IDX2 by 1. Both of these need to be incremented because we are going to use this element, this common element, as an element in the subsequence. Okay, so there's just one recursive call here. That was nice. Otherwise, we have to either ignore the first element of, or the current element from sequence 1, or the current element from sequence 2. So we have 2 options. So we have option 1, which is we ignore the current element of sequence 1. So this becomes LCS recursive sequence 1, sequence 2, IDX1 plus 1, and IDX2. And then we have option 2. This is LCS recursive, once again with sequence 1 and sequence 2. And this time we increment IDX2. Okay, so make sure you understand this piece, because this is really the key here. And then the length of the longest common subsequence is simply the maximum of option 1 and option 2. Okay, and that's it. What may have seemed like a fairly tricky problem, once you start thinking about it recursively, okay, what happens if we simply compare the first 2 and they are equal and they're unequal? Okay, now we need to solve the problem for the remaining. Either we add 1, or we ignore one of the elements, right? Once you get that thought, the recursive thought, then the solution and the code simply presents itself to you. It's just about 7 lines of code. Okay, that's our LCS recursive solution. Now let's test it out. Let's look at a test case T0. Okay, so here we have serendipitous and precipitation as the inputs. Let's call LCS. Let's keep that around so that we can view it later. Let's call LCS recursive on T0. But of course, we need to fetch from T0 the input and get sequence 1 out of the input. And similarly, we need to get the input and get sequence 2 out of the input. You can see it returns the value 7, which is equal to the output, by the way. So if we simply put in here T0 output, and I'm also going to put in this special command called % time. This is going to tell us how long the cell takes to execute. Yeah. So now you can see here that we get back true and the cell takes 495 seconds or half a second to execute. And that's it. So now we have tested this test case. One small thing I can tell you how to improve this slightly is because in T0 of input is a dictionary, and because the names of the elements of the dictionary are sequence 1 and sequence 2, which also match the argument names of LCS recursive. You can see here we have sequence 1 and sequence 2. What you can do is you can simply say ** T0 input, and Python will automatically grab each key. So sequence 1 will be passed as the argument sequence 1, and sequence 2 will be passed as the argument sequence 2. This is a small trick here that helps us reduce the amount of code we need to write. Okay. Now we've tested one test case, but that's not enough. We should be testing all the test cases. So to test all the cases, we can write a for loop for t in tests, etc. But we can do something else too. We can use the evaluate test cases function from Jovian. So from jovian.python.dsa, the module, we will import evaluate test cases. It's a helper function that we've created for you, but it's really simple to write. You can just use a for loop as well. And we call evaluate test cases on the function that we want to test, which is LCS recursive, and the tests that we have, which is LCS tests. And when we do this, it is going to try out each test case. You can see it's tried test case 0, that was a pass. It tried test case 1, and it's also printing out the input, the expected output, and the actual output. The test case 1 was lists, and lists work too because all we have used here is indexing and length, and these are both things that are available in both strings and lists. And this is something that's very nice about Python, the dynamic nature of the functions. Once again, this worked perfectly fine. And then here we have another one, longest in stone. The expected output was 3 and the actual output was 3 as well. Here we have ADS, F, EWAD, and another string. They have nothing in common, so the expected and actual output are both 0. Here's one where one is already a subsequence of another, so the smaller one becomes the longest common subsequence. And then we have an empty string, and then we have 2 empty strings, and finally we have multiple longest common subsequences. We still get back the right output. Now, if any of these failed, you would know exactly what went wrong. For instance, if you had an issue in this case where the 2 of these were empty, then that would tell you that you've probably not handled that empty case properly. And that is why having great test cases is very important. Okay. And we can see the timings for these as well. Each of these took about, 480 milliseconds was the highest. Now, that's still a bit high, I would say, the 480 milliseconds, because we are just looking at sequences serendipitous and precipitation, which are of very short length. Now, if you're looking at a really long sequence, for instance, this technique is used for DNA sequencing, and we were looking at 2 DNA strands or two DNA strings and trying to get the common subsequence out of them. And these can go into thousands or sometimes millions of elements. That would make it rather slow. Okay, so we do want to improve this algorithm further. So let's do that. And before that, we can just commit our work once again. But the first thing before we improve the algorithm is to analyze its complexity. How long does it really take? Okay, and identify any inefficiencies. Now, to analyze the complexity, let's look at an example and let's consider the worst case. Now, when does the worst case occur? Here we've seen that if two elements match, then we simply have one subproblem or one recursive call. But if the two elements or two elements of the sequences don't match, then we have two recursive calls. So if we have two completely distinct sequences where none of the elements match, then each time we will end up with two subproblems. So that becomes the worst case. So the worst case occurs each time we have two subproblems where the sequences have no common elements. And here's an example. This is a sequence of length 6. Here's a sequence of length 8. And this is what the tree will look like. So now we have no longer put the actual sequences. We've simply put what is the length of the string that we start out with. So here we start out with strings of length 6 and 8. And then we say that we either ignore the first character of the first string or the first sequence, or we ignore the first element of the second sequence. And that gives us two subproblems. And this time the sequences have length 5 and 8 in this case, and 6 and 7 in this case. Okay. So we either reduce one from the left or we reduce one from the right. And once again, here we either reduce one from the left or we reduce one from the right. So this way we create a tree, and you can also see that a lot of common trees get created. And that really is what is the inefficiency, and we'll talk about that. But what will happen here is 5, 7 will then call 4, 7 and 5, 6, and 5, 7 here will once again call 4, 7 and 5, 6. And 4, 7 and 4, 7 will get repeated here, and 5, 6 and 5, 6 will get repeated 3 times here. So there's a lot of repeated calls that are going to occur. And you can even see this here at the top. You can see that ALOGY, the problem was called repeatedly. So that's really a source of inefficiency. But now the question becomes that we know that all the leaf nodes will end at 0, 0. That's when the entire tree ends. So can you count the number of leaf nodes? Okay, can you count if you keep expanding this tree completely, expand each of these, don't skip any of them. Can you count the number of leaf nodes? Now, if you count the number of leaf nodes, we know that in a binary tree, the number of leaf nodes, if the number of leaf nodes is L, then the height of the tree is if the number of leaf nodes is n, then the height of the tree is log n. And based on that, we can actually determine the actual size of the tree as well. So we know that to count the number of unique paths from root to leaf will give us the number of leaves, right? So each time we have two choices. We either reduce from the left or we reduce from the right. So to get to 0, 0, we would have to reduce all the elements from the left and we would have to reduce all the elements from the right. That means if you have strings of length or sequences of length m and n, then you would have to make m plus n choices in total, right? And so each time you have to make m plus n choices, and each time you have to choose whether you want to reduce from the left or from the right. So you have two choices and you have to make those two choices m plus n times. That's the right way to put it, really. So that means each time you do two choices, so you have 2 multiplied by 2 multiplied by 2 multiplied by 2, and you keep multiplying that, and you will end up with 2 to the power of m plus n leaf nodes. Okay. So here is an exercise for you. Draw this tree on a piece of paper. Mark out how the number of leaf nodes, how the length of each part is m plus n. Figure that out. And based on that, can you conclude that it takes 2 to the power of m plus n leaves to complete this tree? And if 2 to the power of m plus n is the number of leaves, then the total number of elements in the tree is simply double of that. Once again, this is something that is very easy to verify. You can check it here. For instance, if you just consider these two levels, if you have 2 leaves, then the total number of elements in the tree is 2 plus 1, 3. Actually, it's double minus 1. So 2 into 2, 4, minus 1, 3. If you have 3 levels, you can see here that if you have 4 leaves, then the total number of elements in the tree is 4 into 2, 8, minus 1, 7. And you can see that here. So it follows essentially that we have an exponential number of subproblems. We are calling the recursive function an exponential number of times. And inside the recursive function, we are doing a constant time work. So you can see here that there's no special work that we're doing. All we're doing is some comparison, and we're doing an addition. Both of them are constant time. So we make 2 to the power of m plus n recursive calls. Inside each we do constant work. So the time complexity is order of 2 to the power of m plus n. Okay. That's a rough explanation. We've not gone into a lot of depth because we've covered this over and over in 3 lessons. But the exercise for you is to verify how exactly it is 2 to the power of m plus n. Okay. So that's our recursive solution. And we now know that the time complexity is 2 to the power of m plus n. Let's just copy that over here. And the inefficiency, as we said in this algorithm, is that we are calling the same problem. We're calling the exact same problem. The LCS recursive function is called with idx1 equal to 5 and idx2 equal to 7, and idx1 equal to 5 and idx2 equal to 7 the same time, twice. So each of these sub problems will be called twice, and then each of the sub problems within them will be called twice. And of course, some of these sub problems will once again get shared. So there's a lot of repetition. Now there's a simple solution here, which is simply to remember some of these results. Okay, and this technique is called memoization. And you may also just call it memorization because you're just remembering some of these things, but memoization is a technical term for it. And we remember these solutions in our dictionary called Memo. So what we're going to do is we're going to follow the same recursive strategy, but this time we are going to maintain a dictionary called Memo, and we're going to track intermediate results within the dictionary. And if we find an intermediate result already exists in the dictionary, then we will not compute it again. Okay. So let's see. So now we write LCS memoized, or let's just say LCS memo for short. It takes a sequence 1 and it takes a sequence 2. And this time we create this dictionary called memo. And then we write a function inside it. So we will write a helper function, a recursive helper function inside the LCS memo function, so that it has access to sequence 1 and sequence 2. And we will simply start it out with idx1 as 0 and idx2 as 0 as well. So idx1 will track the position in sequence 1, idx2 will track the position in sequence 2. Now the first thing we do is create, using the 2 indices, create a key. So we are going to create the key idx1, idx2. And if the key is present in the memo, so this is the way to check if a key exists in a dictionary, then we simply return memo of key. Simple. The problem is solved. We don't have to solve this problem because it's already something that we've solved. If it isn't, then we need to solve the problem and save it in the memo. Now here we know that we can now write our same 3 recursive cases. Now if the base case, if idx1 is equal to the length of sequence 1, or idx2 is equal to the length of sequence 2, then we simply set memo of key as 0, because by this point we have reached the end of the strings. There's nothing left for us to compare. Elif idx sequence 1 of idx1 equals sequence 2 of idx2. So in this case, this is the case where the current characters are equal. So this is, if we go up here and look at the tree once again, this is a case like this where the current characters that we are pointing at are equal. So in that case, we simply get the result as 1 plus the result for the remaining with the first character removed. So in this case, we simply set memo of key to 1 plus, we call the recursive function again, recurse idx1 plus 1 and idx2 plus 1. Great. Else, so this is the case where the 2 elements are not equal. So, and this is where we have 2 options. So I'm not going to write the 2 options separately. Let's just do a max directly here. Max, and we say recurse with idx1 plus 1, comma idx2, and recurse with idx1, comma idx2 plus 1. Okay. And finally, from the recurse function, we return memo of key. So we have, whichever case it is, we have computed the result and saved it in the memo. So this time, these computations will not get repeated again and again. And let us now return recurse of 0, 0, because 0, 0 is the entire string. And that's it. And this is the common strategy that you should apply whenever you come up with a recursive solution and you see the inefficiency coming because of the same problem being called again and again and again. This is where you need to apply this technique called memoization, right? And in this technique, you will then be able to simply store intermediate results. So it's really simple. You just create a dictionary and then you add 1 or 2 lines of code here, and you make sure to save the result in that dictionary whenever you compute a result. The next time you don't have to compute it. Okay. And we can test it out. We can test it out with all the test cases. Evaluate the test cases. So LCS memo and LCS tests. And you can see that all the test cases pass. Now, not only do all the test cases pass, you can see that the time taken is now lower. Okay, so that's nice. The time taken is now lower. Now we went from 450 milliseconds. If we just go up here, you can see that it took 480 milliseconds for finding the longest common subsequence between precipitation and serendipitous. But in this case, it only took about 0.234, which is 0.2 milliseconds. So it is 2000 times faster, even for strings of length 7 or 8. And that's a huge boost. Let's analyze the complexity here. Let's look at the complexity. Now, a quick way, an easy way to find the complexity of the solution is to see where the computation, how many times the computation can occur. Now, this is where the bulk of the computation is occurring in a recursive call. And this computation is avoided if we already have something in the memo. Okay. So that means that the only number of computations that we need to do is equal to the maximum number of elements that can end up in the memo. Now, what are the keys in the memo look like? The keys in the memo look like IDX1 and IDX2. Great. And what values can these take? IDX1 can take 0 to m values if m is the length of sequence 1, let's say. And IDX2 can take 0 to n values if n is a sequence length of sequence 2. So in total, the possible number of keys is m times n. The possible number of keys is m times n. The possible number of things that you need to store in the memo is m times n. And for each of them, you do constant work. And then the next time you try to access this, you do not need to do the work. You do not need to call any recursion. You can simply access the memoization, right? So what that tells us is the complexity of this case, and in any memoization case in general, is equal to the number of keys, which in this case is m times n. So the time complexity here is order of m times n. So we've gone from 2 to the power of m plus n, which if m plus n was equal to 30 would be 1 billion, to m time order of m times n. So let's say both strings were 15 and 15. So that would just be 225 operations. So we've gone from 1 billion operations to 225 operations simply by storing intermediate results. And it's a very powerful technique that we apply all the time. So now you can see here that the first time 5,7 is computed, the next time 5,7 does not need to be computed again. And that's why this tree here is actually marked out. So this is the tree for memoization. The first time 4,7 was computed, it never needs to be computed again. So this entire tree of computation gets eliminated. And similarly, this entire tree of computation gets eliminated. We are eliminating from 1 billion computations almost all except 225 computations. So we are left with practically nothing. And that speeds up your algorithm by a huge, huge factor. So that's memoization. And as I said, it's really easy to compute the time complexity of memoization. Just simply count the number of keys, and then just track how much work do you need to compute each key, assuming that you already have the recursive solutions for the remaining. Okay, so how much work do you need to compute each key using some other existing solutions? Now in this case that was constant because all we needed to do was compare and add. Okay, and I'll let you write here a simple optimized plain English explanation of memorization. It's a good exercise to try out. But what we will also look at is another technique called dynamic programming. Now the downside with memorization is that it requires recursive calls. And while it's not a problem for small cases, when you have really large problems, recursion has an overhead. And the overhead for recursion, if you see it this way, is that for this function execution to complete, you need this function execution to complete and this to complete. And for this to complete, you need this to complete and this to complete, right? So the idea here is that for each new recursive call takes more space in the memory, and it also takes longer because now we have to allocate some memory and then set up that function stack, the function stack for the execution of that function. So if you have a large tree, then you're creating hundreds, thousands, or possibly millions of open functions, all of which have their own memory, and that can eat up a lot of memory, and sometimes that can also take longer time. So the solution to replace recursion is iteration. And how do we do that? We do that using a technique called dynamic programming. So we'll do almost the same thing. There are a few changes here. Instead of using a dictionary to track intermediate results, we will create a matrix, because we know that sequence 1, the IDX1 can go from 0 to n, or 0 to n1, let's say, where n1 is the length of sequence 1, and sequence IDX2 can go from 0 to n2, where say n2 is the length of sequence 2. And what we can do is we can use a for loop or a couple of for loops to fill out all these sub problems without having to require a recursion. Okay, and this is how we'll do it. So let's say these are the two strings that we're working with. This is string 1, TACGT, and this is string 2. And this is what DNA sequences look like. So what we'll do is we will create a table of size n plus 1 plus 1, n1 plus 1 and n2 plus 1. So you can see that there are n1 plus 1 rows. So if this is of length n1, these are n1 rows, and then there's an additional row. And similarly, there are n2 plus 1 rows here. So if this is of length n2, there are n2 plus 1 columns. So you can see these are n2 columns, and there is an additional column here. And table of I and j. So let's say table of if I and j are 0, so I is a pointer for the first sequence and j is a pointer for the second sequence. So I selects a row and j selects a column. So table of I and j represents the longest common subsequence of sequence 1 up to I, which means sequence 1. So here, if let's say I was 1 and j was 1, so this represents the longest subsequence of sequence 1 up to I. So all the positions before 1, which means only the 0th position, just t, and sequence 2 up to j, which means all the positions up to the first position, up to 1, so which means only the 0th position, so which means a. Okay, so table 1 and table ij represents the longest common subsequence of these two, of just a and t, which is 0. On the other hand, if we skip ahead a little bit, if we skip ahead to, let's say, this position, you can count here. I goes 0, 1, 2, 3, 4, 5, 6. So this is 6 here. And here we have 0, 1, 2, 3. So this is table of 6, 3. So table of 6, 3 takes the first 6 elements, which is TA, GT, CA, and the first 3 elements, AGA of sequence 2, and it stores the result of the longest common subsequence between these two. Okay, so I'll just let you look at the table and maybe even draw the table on a piece of paper and verify that the length 3 is right. You can see here AGA occurs here. So AGA is a subsequence of TA, GT, CA. So the longest common subsequence between them is 3. Now, what we'll do is we will now compare the next elements of, we'll now compare sequence 1 of I and sequence 2 of j. So let's say we are looking at, let's pick an example. Let's say sequence, let's say I has the value 0, 1, 2, 3, 4. I has the value 0, 1, 2. I has the value 2. And let's say j has the value 1. So 0, 1. So if we compare sequence 1 of I, so which is G, and sequence 2 of j, which is also G, and if they're equal, so if they're equal, then table of I plus 1 and j plus 1, which is this value, right? So remember, I is 2 and j is 1. So table 1 of I plus 1, so table 1 of 3 is 0, 1, 2, 3, and table 1 of I plus 1, j plus 1 is table 1 of 3, and a table of I plus 1 and j plus 1, I being 2 and j being 1, is table 1 of 3 and 2, and table 1 of 3 and 2 is the value 2. So this value is obtained by adding 1 to table 1 of I comma j. So because these two elements are equal, we can then say that if we take the longest common subsequence of TA and A and add 1 to it, that will give us the longest common subsequence of TAG and AG. So the exact same logic as recursion, we have simply now reversed it. So now we're looking at the last element, so that we can keep filling out the last value using some previous values. Okay, so this is one case. Similarly, here's one other case where A and A are equal. So the longest common subsequence between TAGTCA and the longest common subsequence between AGA is 1 plus the longest common subsequence between TAGTC and AG. Okay, 1 plus this value. So that's one case. The other case is if they're not equal. So let's look at this value, for example, over here. So we have TAGT on this side, and then we have, okay, let's look at this one. We have TAGT on this side and we have AGAC on this side. Now T is the element here and C is the element here. They are not equal. So that means the longest common subsequence between these two either does not contain T or it does not contain C. It cannot contain both, obviously, because one of the strings has to end. So if it does not contain T, then it is this result. And if it does not contain C, then it is this result. So we simply take the maximum of these two to get the result for this, if these two elements are not equal. And that is how you fill out the table. You start from the top. The first row is zeros because we have empty strings, and the first column is also zeros because we have empty strings. To fill out an element, you compare if the two elements are equal, and if they are equal, we simply add 1 to the diagonally left top left element. If they are unequal, then we take the maximum of the element above it and the element to the left of it, and that way we fill out the entire table. Okay, so that's the dynamic programming solution. And I know this can seem a little bit complicated. Honestly, I still get confused with dynamic programming a lot of times, and that's why I like to just draw tables and write things out carefully. Okay, and especially you have to be specially careful with indices, because here we are saying that if sequence 1i and sequence 2j are equal, then table 1 of I plus 1 and j plus 1 is 1 plus table ij. So just watch the indices carefully here. But let's implement the solution. Let's implement the dynamic programming solution. So let's say LCS, dynamic programming. So we'll just say DP here. And we have sequence 1 and we have sequence 2. And the first thing we need is we need a table of results. Now this table, for it, let's just grab N1 and N2. So length of sequence 1 and length of sequence 2. And now we need to create a table with all zeros. How do you create a table with all zeros? A way to create a list of zeros is this: 0 for underscore in, let's say N1, and let's give N1 and N2 some values. Now, if you want to create a list of zeros of length n1, you simply say 0 for underscore or 0 for x. You're simply ignoring whatever value you're getting from a range n1, and that's going to give you a list of zeros. But we don't want a list of n1 zeros. We want these want to be rows, so we want each of these to itself be a list of zeros of length n2. So 0 for x in range n2. And now we have, you can see that we have 5 rows, 1, 2, 3, 4, 5. Then we have 7 columns, 1, 2, 3, 4, 5, 6, 7. So this is the table that we want to create initially. Okay. Now this is the table that we've created. This is going to be this exact same table. And we're simply going to start each string from position 1 this time, not from position 0, because we want to have this additional row where we don't consider either of these. That just makes computations a little easier. Now we say for idx1 in len idx1 in range n1, so that's going to iterate over the rows, and then for idx2 in range n2, and that's going to iterate over the columns. And first we compare if sequence 1 of idx1 is equal to sequence 2 of idx2. If they're equal, then we can fill out table of I plus 1 and j plus 1 as 1 plus table of ij. Okay, and we can see this we can see this here. Suppose the first elements were equal. So suppose idx1 was 0 and idx2 was also 0. Suppose they were equal. Then this value should be 1. So this value should be 1 plus the diagonally top element. And that holds true anywhere within the list. So wherever you have two elements equal, like g and g are equal here. So this value is 1 plus this value. Else we have table I plus 1 and j plus 1 is max of table I comma j plus 1. So you stay in the same row, or you go to the previous row, or you go to the previous column, which is table of I plus 1 comma j, and this is the previous column. Okay, so this is this case where g and a are not equal. So if g and a are not equal, then we take the maximum of these two values, and that's it. That is going to fill up the table for us. And then we simply say return table. We simply want the bottom right element, so we can simply say return table minus 1 minus 1. So this is going to get the last row, last column, and that's our dynamic programming solution. Let's do evaluate test cases here. Okay, it turns out there's no I. Okay, let's just call this I and j. Turns out idx1 is not defined. Let's just make these I and j. Now that we're doing this coding live, you can see that even after a decade of coding, I still make all of these issues. It says a list index is out of range. So it seems like I plus 1 and j plus 1. That's because, remember, we need an additional row and an additional column to track the case where either of the strings is empty. So we need to get range n2 plus 1 here, and we need to get range n1 plus 1 here. Okay, and that's why it helps to have test cases, so that you can fix all of these issues. Now you have test case 0, it passes, and test case 1, 2, 3, all of them pass. You can see that all test cases have passed. And you can also verify that the amount of time it took is now lower than the amount of time it took for memoization. Okay, and so that's the dynamic programming approach. You simply create a table and you fill out the table. Sometimes just working with indices within the table can get confusing. So it helps to work with it on paper and make it clear to yourself, and then write it in English. So that's why we've written it in plain English here. And now an exercise for you is to verify that the complexity of this dynamic programming approach is order of n1 times n2. So which is the same as memoization. And it's actually more straightforward to see here because you have two for loops. And then each of these for loops, you are simply doing a comparison and an addition. And there's not even any recursion to there's not even any recursion for you to worry about. So you just do a comparison and you do an addition or you take a maximum. Pretty straightforward. So order of n1 times n2, and it does not even invoke another function. So it does not take up too much memory. It does not take up too much time. It's very, very efficient. And this is how you solve pretty much every dynamic programming problem. You write a recursive solution, you come up with a brute force solution, and keep in mind that recursion is almost always the way to go about creating a brute force solution. So you come up with a recursive solution, and then you draw the recursion tree. And if you see that the same subproblem is being called again and again, that is a point where you can introduce memoization. So you introduce memoization, and sometimes you can just write the memoized solution and that's enough because it's easy to reason about. You just put in a memo and you're done with it. Even the interviewer or the coding assessment will accept that solution. But in some cases, you will be asked to then remove the recursion and write it in an iterative fashion. And that is when then you have to start drawing a table and think about what are the rows and columns in that table need to represent. So here the ijth element of the table represented the first I elements of sequence 1 and the first j elements of sequence 2. What is the longest subsequence between them? And we use that to build the next row and the next column. And we then filled out the entire table and we simply used the last value. Okay. Now, again, this is not very straightforward how to come up with this, and the way you do that is by solving problems. So if you solve 5 to 10 dynamic programming problems, you will get some intuition about how to build the tables, and it's always very helpful to solve it on pen and paper first, especially with dynamic programming, so that it's clear to you what each element of the table represents. Otherwise you may make a lot of off by one errors, like missing the +1 here or missing the +1 here, and get confused, just like I did pretty much. And that's the time complexity is pretty straightforward. In most cases, it is simply the size of the table, but sometimes you may have to do more than constant work here. So keep that in mind. See what it is that you're doing inside your loop. Now inside your loop, if you have to go back and check the entire length of the string, so that will introduce another factor into the equation. So keep that in mind. But in most cases, counting the iterations should be good enough to give you an idea of the time complexity. Okay, so that's the first problem, and let us just commit this, and now it's saved to my profile. So if I just open this up here, you can see that now I have this notebook called longest common subsequences, and I can share it online. Whenever you work on a notebook, it's always a good idea to make it public, put it up on Jovian. All you need to do is run jovian.commit and share it online. Just press the share button, and then you can share it on Twitter, LinkedIn, Facebook, or wherever you like. So that's the first problem that we looked at. Now let's come back to lesson 4. And by the way, the problems that we're talking about, all the problem statements, the graphs, the images, you can see them in the second link here. But we will once again open up the problem solving template. And now we'll use it for the second problem. So let me run this once again. And we're going to look at the second problem, which is the knapsack problem. So let's read the knapsack problem. It's also called the 0-1 knapsack problem. There are many variations of this problem, but here's one way to state it that you might come across, or something similar. You are in charge of selecting a football or a soccer team from a large pool of players, and each player has a cost and a rating. So there's a selection going on. You have to come up with a team for this year, and you have a large pool of players. Each player has a cost and each player has a rating. Now you have a limited budget, so you need to build a team within the budget. So what is the highest total rating of a team that you can create which fits within your budget? Okay, so this is the question here. You have to maximize the total rating, but fit it fit the total cost within your budget. So you have two variables here, rating and variables. Rating needs to be maximized. Cost needs to be simply optimized to the extent that it fits in the budget. And just a simplifying assumption here is that you can assume that there is no minimum or maximum team size. This is simplification. And later you can introduce a criteria there as well, that you want to build a team of exactly 10 people and see if you can also solve that problem in a way. So that's the knapsack problem. Let's copy it over. And here's a Jupyter notebook, a fresh problem solving template. Let's simply change the title here. It is also called the 0-1 knapsack problem because each item can either be chosen or not chosen. And let's give it a project name here too. Let's commit it and let's paste the problem statement here. Okay, so that's the problem statement, and this is a specific or a special form of a more general problem statement. And we look at the general problem statement in a second when we try to state the problem clearly. But here's once again the systematic strategy we'll apply. We will state the problem clearly, identify the input and output formats, come up with some example inputs and outputs, and try to cover all the edge cases. Then we will come up with a correct solution for the problem and state the solution in plain English. It just has to be simple, correct solution, not too complex. Then we apply the right technique to overcome the inefficiency, and then we analyze the algorithm and identify any inefficiencies after implementing the solution. And finally, we apply the right technique to overcome the inefficiency, and then repeat the process of stating the solution, implementing it, and analyzing it. So to state the problem clearly, what we can do is we can abstract out the problem in more general terms, and that is what is stated here. And let's just grab that and we'll take a look. So here we are given n elements, and each of which has a weight and a profit. So you have n elements, and here's the profit of each element, and here's the weight you can of each element. So you need to determine the maximum profit that can be obtained by selecting a subset of the elements weighing no more than a given weight W. So you have a capacity, a maximum capacity. Let's say the maximum capacity is 15. And you have to select certain elements so that you fill out the total weight is no more than the capacity and the total profit is maximized. And this is why it's called the knapsack problem. It's assuming here you have a bag or a knapsack with a capacity of 15 kilograms, and these are the weights of the items and these are the profits. Now in this case, you can see in this example, the optimal selection is these 4 elements which have the weights 5, 3, 2 and 5, so that you fill out the total capacity of 16 or 15, and the solution or the maximum profit that you can obtain is 7 plus 4 11 plus 5 16 plus 3 19. Now you can try other combinations and verify that this is actually the best solution. Do give it a shot. So what are the inputs here? So we have, it's pretty clear, we have an input weights. So these are the weights of the, this is a list of numbers containing weights. And then you have profits, a list of numbers containing profits, and this should have the same length as weights. And then finally you have a capacity, the maximum weight allowed, and there you go. And now we have outputs. So now the output would simply be the max profit. So this is the maximum profit that can be obtained by selecting elements of total weight no more than W, or no more than capacity. Okay, great. So that gives us a pretty good starting point. Now we can write a function signature here. So we write max, let's say def max profit, and we can give it weights, and we can give it profits, and we can give it a capacity, and we pass. So now we have defined the problem. We have identified input and output formats. Now we need to come up with some example inputs and test cases. Once again, we have listed out a few test cases here. So we will have a few generic test cases where you have just a random set of weights and profits, and you identify the knapsack, the optimal solution. Then here's one option where all of the elements can be included. You can take everything. Here's another option where none of the elements can be included. You have to think about all these scenarios. Here's one where only one of the elements can be included. Then you may also think about areas where you do not use the complete capacity. Okay, you do not use the complete capacity because the optimal solution is actually taking a lower capacity. So there may be a way to fill out to capacity, but that may have a lower profit than another option which takes less than the complete capacity but has a higher profit. So think about some cases here. Think about some good test cases here. And I will just copy over these for now. And then what we'll do is we will express these test cases once again as dictionaries. So you have test 0, test 1, test 2, all of these expressed as dictionaries, and these are covering all the test cases that I mentioned here. You can see here are some weights and some profits, and the capacity is 165, and then the optimal solution is 309. Now we are simply asking here for the optimal solution, the maximum profit that can be obtained, but an extension of this problem is to identify which are the elements that should be chosen. And it's a simple extension. It's a good exercise for you to try out, and you can discuss it in the forums. We have test 0, test 1, test 2, test 3, and 4 and 5. So we have a total of six test cases. Let's copy over these test cases here. And let's put them here into a single string, and that gives us the test cases. Okay. Now coming up with a solution. So once again, the first step is to try and come up with a recursive solution. And a recursive solution is again quite straightforward. We'll write a recursive function, max profit, that given an index. So this time we have just one sequence. So given an index within the sequence. So let's say you have an index IDX. It computes the maximum profit that can be obtained using the elements from IDX onwards. So 3, 1, 5, 4, 7, using all of these elements IDX onwards. The maximum profit that can be obtained, right? And using a given capacity. So it will take an index. So it will take an index and a capacity. So if let's say the IDX is 1, so it will then look at just these elements. And if the capacity is 10, so it will try to fill the capacity of 10. And that's a recursive function. And why are we creating a recursive function like this? There's a simple reason. Now suppose IDX has the value 1 and the capacity is 10, or let's say the capacity is 3. Then the weight of this element is greater than the capacity. So that means it cannot show up. It cannot be selected because it cannot fit inside the bag, the knapsack that we have. So then the solution for this sub problem with IDX equal to 1 and capacity equal to 3 is same as the solution for this sub problem with this element removed, because you cannot include this element within the knapsack, right? So if you remove this element and simply consider these elements, the remaining elements, which essentially means IDX plus 1. So max profit of IDX plus 1, profit of weights IDX plus 1, profits IDX plus 1, and capacity is the answer for max profit of weights IDX, profits IDX, and capacity, because the current weight 5 is greater than the capacity 3, which the recursive function has been invoked with. So that's one option. But the more general case is that you have enough capacity. So let's say you have a capacity of 10. Recursion was called with a capacity of 10. and you are at IDX 1. So then you have two choices. Either you include this element in your knapsack, or you do not include this element in your knapsack, because you don't know whether the optimal solution will have this element or not. So you try both. So there are two possibilities. We either pick weights IDX, this element, or we don't. And what we can do is we can simply compute the result in both cases and pick the maximum. So if we don't pick weights IDX, then once again, if we don't pick this element, so the capacity remains the same. Let's say the capacity was 10. So we simply try out to fill out the capacity of 10 using the remaining elements. So we simply call max profit with weights IDX plus 1, profits IDX plus 1 onwards, and the remaining capacity, which is 10. But if we do pick the element, if we pick the element and we had a capacity of 10, then the solution, the best solution in this case, will have a profit 3 more than the solution for this case. And since we also used up some capacity, so we need to add 3 in the profit and we need to subtract 5 from the capacity, right? So if we pick weights IDX, then the maximum profit for this case is profits of IDX plus max profit of weights IDX plus 1 onwards, profits IDX plus 1 onwards. But because we've used up some capacity, we reduce the capacity in the recursive call. Okay. And that is why a recursive call takes both an index and a capacity. Okay. I hope that makes sense. So here's a recursive tree that tells you the same thing. We start at the first index and we have the capacity. And if we don't pick the first element, then the answer is simply the best solution for second index onwards with the same capacity. If we do pick the first element, then the answer is the second solution onwards with the reduced capacity with a profit added. Okay. And then we simply take the maximum of these two cases. So we call these two recursive calls, and then we simply take the maximum of these two cases to get back the final result or the final best answer. And the final end case is that if we've reached the end, if weights IDX onwards is empty, if the index that we're tracking has reached the very end, then irrespective of what the capacity is, the maximum profit is in that case is 0. So let's try and implement this now. Let's copy this over as the explanation. And let's try and implement the solution. Let's call it max profit recursive. And this is going to take a set of weights. It is going to take a set of profits, and it is going to take a capacity, and it's also going to take an index, which the index will start out at 0. So now if the index is, we start with the base case. So if IDX equals the length of weights, so in this case there's nothing left to do. We simply return 0 because we don't have any more elements. Then we check if the weights IDX is, so the current element is greater in weight than the capacity, then it's a pretty straightforward solution. We simply return max profit recursive of weights, profits, capacity plus 1, capacity and IDX plus 1. So we simply ignore this element because we cannot fit it in the capacity that we have. Else we have two options. So we have option 1. Option 1 is, even though it can fit within the bag, we don't take it. We because the optimal solution may still not have it. Just because it fits does not mean we should take it. So we look at the option 1, which is once again the same as this, where we ignore this element. And then we look at option 2. In option 2, we actually put this element into the bag. So since we are putting this element into the bag, then we get profit from it. So we get profits of IDX, and then we call max profits recursive. And this time we call it with weights and profits. And now the capacity has reduced a little bit because we have taken this element. So now we need to fill the remaining we need to fill the bag with the remaining elements from IDX plus 1 onwards with a limited capacity of capacity minus weights of IDX. And then finally, we just put in IDX plus 1 so that we can start calculating the solution from the next element onwards. So that's max profit recursive. Again, not very difficult. It is just about 6-7 lines of code. And let's try it out. Here's test 0. Let's try max profit recursive with test 0 input. And we need to get weights, capacity and profit, all of these out of it. The simple way to do that is simply to put in star and we'll get back all of these will get passed in. Capacity will get passed in as a capacity parameter, in weights will get passed in as the weights parameter, and profits as the profits parameter. Okay, so we've encountered an error, and that's completely fine. Completely fine to encounter an error. I see. So what we've done here is we have not really taken the maximum of these two. We've just defined the two options. So we do need to take max of option 1 and option 2. Okay. Once again, this is why having test cases helps. And you can see that now we call max profit, and we can also add a timer here. So max profit, it takes 210 microseconds, but it returns a result 309. Great. We get back the result 309 here, which is what we expected. So our function is working correctly. We can even evaluate it on all the test cases. So from jovian.python DSA, we import evaluate test cases. And then we simply call evaluate test cases on all the inputs. So we pass in max profit recursive, and then we pass in all the test cases as tests. Now you can see that we have these test cases, and each test case seems to be passing just fine. All 6 test cases have passed, and these are the times they took. So that's your recursive solution. Pretty straightforward. Once you reason it out, once you maybe just look at an example, draw a tree of recursion yourself, work it out on paper, the code is in fact in most cases fairly simple. And this is what the recursion tree looks like. Each time we make a choice to either include the element or not include the element. And now you can reason the complexity very easily, because now we have n elements. For each one we keep making this choice. So that means we end up with 2 to the power n leaves. And from there it follows that the complexity of the recursive algorithm is order of 2 to the power n, right? So it could be 2 times or c times 2 to the power n, but and in the big O notation, it's order of 2 to the power of n. So it is exponential in complexity. And why is it exponential in complexity? Once again, it's a possibility here that we may be computing a lot of things repeatedly because we are creating so many of these sub problems. So it's possible that we may be recomputing a lot of data here. So now the task for you, or an exercise for you, is to write the memoized version of this. So what is it that you need to memoize? Now the trick here is to look at what is changing within the recursive calls. So now in max profit recursive, you can see that weights and profits remains the same, but it's the capacity and the IDX that change. So you can take the capacity comma the index, the IDX, as the key in your memoization dictionary. And each time you compute, so each time, let's say you compute this, or you compute this, or you compute this, store the result in the dictionary before returning it. And then at the beginning of the recursive function, check within the dictionary if this value is already present. Okay. So remember what we did for longest common subsequence. We defined a recursive function internally. We defined a dictionary internally. And the recursive function kept either checking the dictionary or filling the dictionary if it could not find a value. And that could eliminate a lot of the repeated work in your problem. Okay. So that's the challenge for you to try out, implement the memoized solution. And what we'll do is we will go ahead and we will implement the dynamic programming solution. So let's just commit our work once again. And we've analyzed the algorithm's complexity in recursion. It's order 2 to the power of n. In memoization, now that's an exercise for you. What do you think the complexity will be? But let's apply dynamic programming. So let's look at a dynamic programming solution. Now, once again, for dynamic programming, you have to create a table. You almost always have to create a table for dynamic programming. And in this case, we can see that there are n elements. So there are n rows within the table because we have n elements to choose from. And we have a number of columns going from 0 to capacity plus 1, going from 0 to capacity. And that's why there are a total of capacity plus 1 columns. And in fact, what we can do is we can also include another column at the top here, another row at the top here, which is not shown here. But what n represents, n is the number of elements. So what n represents, or what a particular element in the table represents. So table of I, C, what it represents is the maximum profit that can be obtained using the first I elements if the maximum capacity is C. Okay. So if your maximum capacity is C, let's say your maximum capacity is 3, what is the maximum profit that you can obtain using the first 2 elements? So here, let's say we are at this position. So using the first 2 elements of the list within this capacity. Okay. So the first 2 elements have weights 1 and 2 and the capacity is 3. So you can actually pick, the first 2 elements have weights 2 and 3 and the capacity is 3. So you either pick this element or pick this element. Now, if you pick this element, the profit is 1. And if you pick this element, the profit is 2. So the solution is to pick this element and you get, you fill the capacity 3 and you get a profit of 2. You cannot pick both because your capacity is 3. Okay. So that's the logic here. A very simple visual representation. Now remember that there will also be a 0th row here, which we have not shown, but this is something that should be here, another 0th row. So the 0th row represents that you've not picked any of the elements. And if you don't pick any of the elements, it is simply going to contain all zeros, and that's why it's not shown here. The first row assumes that you can pick only the first element. So you can't pick the first element till a capacity of 2, and then from a capacity of 2 onwards, you pick the first element, and that has the maximum capacity of 1, the maximum profit of 1. The second row, or the row number 2, with index 2, represents the fact that you can pick both of these elements. And if you can pick both of these elements, once again at capacity 0, none of them can be picked. At capacity 1, none of them can be picked. At capacity 2, this element can be picked, which has weight 2, and it gives you a maximum profit of 1. At capacity 3, this element can also be picked. So now you have a choice to pick between the 2 of these. So you might as well better pick this one because this is going to give you higher profit. And then finally, when the capacity becomes 5, you can pick both of these elements. And you can pick both of these elements, and that is going to give you a profit of 2 plus 1, 3. And so on. So you keep filling out this table for each step here, or for each set of first I elements. You fill out the capacity table, and then you use the information to fill out the next row and the next column, and so on. Okay. And finally, what we need is using all the elements and using the maximum capacity that we have, what is the maximum profit that we can obtain? So the last element of the table will give you the result. Okay. So what does the logic look like? We will fill the table row by row and column by column. Now, if table of I, C, let's say this is a certain position here, table of I, C can be filled using some values in the row above it. Okay. Now, if you look at the table of I, C, you look at this element, for example. Yeah, let's look at this element here. So in here, C has the value 3, and then I has the value 0, which is a row that is not shown. 1, 2, 3, 4. So I has the value 4 and C has the value 3. So if weights of I is greater than C, So 0, 1, 2, 3, 4. If this weight, so this weight, the weight of this element is greater than the capacity. So the weight of this element is 4. It is greater than the capacity. Then this element cannot show up in this maximum profit. Why? Because its weight is greater than the capacity. So obviously it cannot show up in the maximum profit. Now, if it cannot show up in the maximum profit, then this cell can be filled using the value above it, because in any case you cannot put in this element. So you might as well get the result by using the first 3 elements. And in that case, the value of this cell is obtained from the value of the cell above it. That's one case. Now, on the other hand, let's come here. You come to this case, to this cell. To fill this cell, because you have a capacity of 4, you have the option of either choosing this element or of not choosing this element. Now, if you do choose this element, let's say you choose this element with a capacity of 4. With a capacity of 4, you get back a profit of 9. And now you have no more capacity left to fill more elements. On the other hand, if you do not choose this element, then that's the same as this value, because if you do not choose this element, then you have to fill the capacity of 4 using the first 3 elements, and that simply gives you the same highest profit as the previous cell, right? So you just consider these 2 cases, whether we choose the element or we do not choose the element. Now, if you do not choose the element, the value comes from above. If you choose the element, then the value comes from where? Let's see. If you choose the element, the profit of 9 comes, and you filled out the capacity 4, so you have no remaining capacity. But on the other hand, if the capacity was 6 and you choose the element, then you have chosen the element and you've used up the capacity 4. So you can still use the previous 3 elements to fill the remaining capacity, which is 6 minus 4, so which is a capacity of 2. So you can go back to the previous row and check the capacity 2 and see how much was the maximum profit that you can obtain with capacity 2. And it turns out that with capacity 2, using the first 3 elements, you can obtain a maximum profit of 1. So the maximum profit here, when you choose the element, is 9 plus 1, 10. Similarly here, the maximum profit that can be obtained if you choose the element is 9 plus 7 minus, plus from the previous row, you pick the element with a capacity 7 minus 4, which is 3. So 9 plus 5, 14. Okay. So that's the logic here. Sometimes you choose the element, sometimes you don't choose the element. And in fact, the result of this cell is simply the maximum of either not choosing the elements, the maximum of this cell, or choosing the element and subtracting the weight, which is 6 minus 4, 2. So maximum of this and that. Okay. So let's implement this same dynamic programming solution. Once again, do work this out on paper. It really helps to work it out on paper. But let's say we have max profit DP, the dynamic programming solution. We have weights, we have profits, and we have a capacity. And then let's say N is len weights. So we need to create a table. So this is our table. Our table contains n rows. So we have len n, and then for each of the rows we have capacity plus 1. Oh, we contain n plus 1 rows, remember? So we also want to consider the case where we don't take any of the elements. And it is filled with zeros, and the number of columns is capacity plus 1 to check the values from 0 to capacity. So that's our table right now. You can check what this capacity looks like. Let's say n and capacity have the values here. N in this case is 5 and capacity is 10. Oh, we don't need a len here. We don't need a len here as well. It's all perfectly natural to make these mistakes. This should be range, not len. So this should be a range, and this should be a range too. Yeah. Now you can see that we have created n rows or n plus 1 rows. So one for each of these, and then one more row above containing all, which will contain all zeros. This is in the case where we don't pick any of the elements. And then we've created 11 columns. So this is for capacity 0. So again, the first column will also contain all zeros. And this is something that you will often see in dynamic programming. You will have an additional row at the beginning or at the end containing all zeros. And that is simply to make your calculations or computations easier. But what that will lead to is off by 1 error. So you need to be very careful while doing this. And now we'll fill out this value using either this value or by subtracting the weight of the element that's here and getting a value from the previous row. So now we start iterating. So now we say for I in range n and for j in range c. Let's just say for c in range capacity, it should be capacity. Table of I comma c, and it's actually going to be I plus 1 and c plus 1 because we have these additional rows and columns. Table of I plus 1 comma c plus 1 is, there are two cases here. If weights of I is greater than c, the current capacity, then we can simply look at the previous row. So which is this case. Let's say the weight 3 is greater than the current capacity 2. So then we simply copy over the value from the previous row, the same column. So we just say table of I comma c plus 1, we see. So our capacity should go from the value of 1 because we don't want to affect the first column. So our capacity goes from the value of 1 to a value of 10. So capacity C goes from the range of 1 to capacity. And if the weights I is greater than the capacity, then we cannot fill the table. On the other hand, if it fits within the capacity, then we have two options. So table of I plus 1 comma C has two options. So one is we don't use the current element. And that gives us table IC once again. The other option is we use the current element. So we get profit from the current element. So profits I, but we do not get profits, that reduces the capacity. So we then have to pick table of I, but now we have to pick C minus weights of I. Okay. And that should fill out the entire table pretty much. And that's a nice thing about dynamic programming. You simply just have to write this one solution or this one recurrence and be careful about it. And everything else is taken care of by this loop here. And now we simply return table of -1 and -1. And let's see if that works. It's likely that there are some issues here, but let's see. We have test cases. Max profit DP with the tests that we have. Great. So we are seeing an issue already. I see here that this should be range and this should be range. Okay. One thing that we haven't done here is well, it seems like our solution is always 0. This should be capacity plus 1, so that this takes all the values from 0 to capacity, right? So C, the iterator, should take the values from 1, 2, 3, 4 all the way up to the maximum capacity, and the range does not end. So the range does not include the end value. So you need to put capacity plus 1 here. Okay. Now with that out of the way, you see once again these off by 1 errors are always going to bug you with dynamic programming. I've probably solved 50 or 100 problems in dynamic programming, but I still make these errors. But with that out of the way, you can see now that each of the test cases seems to pass. Now there may be other cases which you have not accounted for, but overall we've covered all the test cases here and we've ended up with now a dynamic programming solution. And I'll let you figure out the complexity here, but once again, it's pretty straightforward. because we are filling up this table, and filling up this table simply requires this constant amount of work, which is a comparison and then potentially another comparison and an addition and a subtraction. So like 4 or 5 operations. So you have this n times n, you have this n times capacity. So where n is the length of weights and capacity, or w is the total capacity. So n times w is the number of iterations, and that really also is the complexity, the time complexity of the algorithm. So that's the knapsack problem. And now what you can do is try and figure out not just what is the maximum value, but also figure out what are the actual elements that were chosen. Now you can do this for the knapsack problem, and you can do this for the longest subsequence problem. Figure out the actual longest subsequence, and it should be possible to do that with just a small modification. Now use the forum. If you have any questions about the contents of this lecture, go back to the lesson page and open up the course community forum here. You can see here that this is the lesson 4 recursion and dynamic programming lesson. You can post your question here, and you can also discuss ideas on how to figure out what the longest common subsequence is and what the best selection for the knapsack problem is. So what do you do next? Well, you can review the lecture video and execute the Jupyter notebook. The next step is also to complete the assignment. Now we have released assignments 1 and 2 so far. If you go back on the lesson page, you will find lessons, you will find assignments 1 and 2, and you can work on them. There is sufficient time, and also work on optional questions, and do participate in forum discussions, and if possible join or start a study group too. That's a great way to stay motivated. This was lesson 4 of data structures and algorithms in Python. Thanks, and talk to you soon. Hello and welcome to Data Structures and Algorithms in Python. This is an online certification course being conducted by Jovian. Today we are on lesson 5, graph algorithms like BFS, DFS, and shortest paths. My name is Akash and I am your instructor. You can find me on Twitter on @AkashNS. If you follow along with this course and complete all the assignments and build a course project, you can earn a verified certificate of accomplishment for this course. So with that, let's get started. The first thing we'll do is go to the course website, pythondsa.com. Now you can point your browser to pythondsa.com to open up the course page. And on the course page, you can enroll for the course and you can view all the previous lessons and assignments. So do check it out, and do check out the course project as well. But for now, we'll open up lesson 5, graph algorithms. Now on this page, you can watch a video for the lesson later, the same video that you're watching right now. And you can also catch a Hindi version if you wish. And here is the code that we are going to use today. The first notebook under the heading notebooks. So let's open it up. And this is a Jupyter notebook hosted on Jovian. You should be familiar with it by now, but here you can see that there are some explanations and then there are some code cells where we can write some code. You can see that there's some code here. Now to actually execute and edit this code, we will need to run this notebook. And you can find the instructions to run the notebook right here. But the simplest way to do it is to click run and select run on binder. Now this will take a second or two, but this will take your Jupyter notebook and create a new machine in the cloud and send your Jupyter notebook to that machine for execution. This is a free service that you can access via Jovian. You can also run this notebook on your own computer directly if you wish. So for that, you can check the run locally option here. Okay. So our Jupyter notebook server is now ready. So we can now start editing and writing some code. Let's just go full screen here. Okay, so the topic today is graph algorithms, BFS, DFS, and shortest paths using Python. Now, before we talk about graph algorithms, let's just try to understand intuitively what graphs are. Now, here's an example of a graph in the real world. So this is the railway map of India. You can see here all the train stations that you have in India. They're represented using these black dots, points. They're also labeled. So each train station points to a city or a village. So all these are also labeled. And then you can see connections between these stations. So these are, as you might guess, railway lines. And you see that there are 3 or 4 colors involved. So these colors could represent different types of railway lines, like different gauge, meter gauge, broad gauge, etc. Or these could represent different zones. So there's some information contained in the connections as well. Now, another important thing is that each railway line between 2 cities will also have a certain length. So that's what a graph is roughly. And the kind of questions that you may want to ask here is, for example, is there a path from New Delhi to Hyderabad? So given this information, first of all, the question is, how do you even represent all this information? Because you have so many railway lines, connections between different cities, so many hundreds of cities. How do you even represent this so that you can start writing algorithms to answer these questions, right? So if you're building a train search website, then you would have to answer, given New Delhi and Hyderabad, is there a way to get from New Delhi to Hyderabad? Okay, that's the first question that you might ask. Now, if there is a way, then the next question might be that what is the path with the shortest number of stops? So do you go this way for the shortest number of stops, or do you go this way, or do you go this way? Another question could be, what is the path with the shortest distance, right? So sometimes if you measure the distance and if you measure the number of stations, the number of stops, they may be different along different paths, and one may be greater than the other in certain cases. So those are the kind of questions that we want to ask and answer today. Oh, another question could be, what are all the stations reachable from New Delhi within 1 stop or 2 stops or 3 stops or 10 stops? So those are the kind of questions we'll try and answer. And for that, we need a way to represent graphs in a more abstract fashion, because this same question can be asked in a different context. For instance, here we are looking at flight routes, international flight routes. Now, once again, you can ask the exact same thing here. Is there a way to get from New Delhi to Vancouver? Now, if there is, then how many stops will that require? What is the minimum number of stops we can take to get from New Delhi to Vancouver? Or what is the minimum time it might take? Maybe if you are okay with taking multiple stops, but you want to minimize the time taken or the distance traveled because you're concerned with the miles for some reason. Another thing that you could ask is, what is the minimum cost if there is a cost along each route? Okay. Now here's one more example from a very different domain. This is hyperlinks, or the internet essentially. So you can see here you have a whole bunch of websites and you have links on websites. Now links on websites point to other websites, and in this case it is a one-way connection. You can see that from this particular course website we have a link to IBM, but from IBM you may not have a link to this course website. Now that's an interesting thing. That's a slight variation here. And this is called a directed graph because each connection here has a particular direction. Now this is again interesting to ask, is there a way to navigate from cs.umass.edu to Ithaca weather? If there is, what is the shortest way? What does that path look like? So those are the kind of questions that we want to answer today. And to do that, we will need a more abstract representation of graphs. And we'll start with the simplest possible representation where you have certain points, or what we will call nodes or vertices. So these are 2 terms that are used for these points. So nodes or vertices. So a graph has certain nodes or vertices. And just to make things easy, these could be cities, or these could be web pages, or these could be something else. But just to make things easy, what we'll do is we will number the nodes. So in our graph, if we have 10 nodes, then we will number the nodes from 0 to 9. Okay, and they can be numbered completely arbitrarily. There's no reason to number this 0 or number this 1. What's more important is that we should use up all the numbers from 0 to n minus 1 if we are dealing with n nodes. Now, why do we do that? We'll see in a moment when we try to represent graphs using certain data structures like adjacency list, etc. But we want to number our nodes from 0 to n-1, and this number is arbitrary. This 1 doesn't represent anything in the sense that 1 being greater than 0 or so on. Okay. So these nodes have labels, and then you have edges between nodes. So an edge is simply a pair. An edge is simply something like 1, 2. So a pair 1, 2 tells you that there is an edge between the node 1 and node 2. Okay. Now, as we move forward, we will also store some information within an edge, and we will call that weight of an edge. And we will also later look at directed edges, and those will get us directed graphs. But let's start with this, and let's see how we can now represent with this basic structure, how we can represent a graph. So we can represent a graph using two variables. So one is called a number of nodes, and the number of nodes is in this case 5. And then we can represent the edges using a list of pairs. So in this case, the pairs are 0, 1. In this case, the pairs are 0, 1, that's an edge. Then 0, 4, that's an edge too. Then we have 1, 2. So 1 is connected to 2. And the edge in this case is bidirectional. So when we're saying 0, 1, we're saying it automatically says that 1 and 0 are also connected, right? So 1, 2, and then we have 2, 3. And which order we write these in doesn't matter. We could have just written 3, 2 here as well. Oh, we also have 1, 3. And then we have 1, 4. Great. And then finally, we have 3, 4. Okay. So this is how we represent this data structure. What we've drawn here is now represented in code using these two variables. And we can check here if we simply print the number of nodes and the length of edges, we can verify if this is roughly correct. So you see we have 5 nodes and we have 1, 2, 3, 4, 5, 6, 7 edges. Okay, seems right to me. There may be a mistake here, but roughly we have set things up correctly. Okay. Now the question becomes, is this representation good enough? Now this representation is good enough if you want to convey the structure of a graph to someone. I could give you these two variables and then without showing you this image, and you could use this information to draw the graph on a piece of paper. So this representation is complete. It provides all the information about the graph, but it may not be efficient. For example, if you want to find out which nodes the node 1 is connected to, we would have to iterate over the entire list of edges. We would have to go through this one and then check if either of these is 1 and check if either of these is 1 and so on. So that makes it very tricky to access any information efficiently. Rather, it'll be much nicer to just look at a list of nodes that 1 is connected to in some way and go from there. Now, if you want to find the shortest path, we would first have to find all the nodes that 1 is connected to. And then for each of those, we would have to find their neighbors. And then for each of those, we would have to find their neighbors and so on. So it would get pretty tedious to go through the list so many times. So that's why, and by the way, by a neighbor, we mean two nodes that are connected by an edge. So 0 and 1 are neighbors, but 0 and 2 are not neighbors. Okay, so that's a very simple nomenclature that we can use. And what we can say is if we track the path, we say 0, 1, 2, and if there is an edge between both of them, we say that 0, 1, 2 is a path. So 0, 1, 2 in this case is a path, but 3, 0, 1 is not a path because there is no path, but there's no edge between 3 and 0. Okay. And we'll see what we mean by paths and neighbors and so on in some time. But to work with graphs more efficiently, we will represent them using what's called an adjacency list. Now, the name, it explains what it contains. So the adjacency list contains a list for each node, and it contains a list of all the nodes that are adjacent to that node. Now, again, adjacency is the same as adjacent is same as neighbor. So if for each node, so for example, for the node 0, we maintain a list and that list contains the numbers 1 and 4, indicating that 0 is adjacent to, or 0 is a neighbor of, or 0 is connected via a direct edge to 1 and 4. So that's why you have 1 and 4 here. And then 1 is connected to 0, 2, 3, and 4. You can see that 1 is connected to 0, 2, 3, and 4. Similarly, 2 is connected to 1 and 3, 3 is connected to 1, 2, 4, and 4 is connected to 0, 1, 3. Now this is more convenient for sure. One, because since this is a list, if you want to find, let's say, which nodes 2 is connected to, we can directly access the index 2 within the list. And this is why we number the vertices, or number the nodes from 0 to n-1, so that we can access them directly in an adjacency list, right? So we directly access the numbers stored next to 2, and so we have 1 and 3 here. So that's what makes it convenient. And one important thing to notice here is that each edge occurs twice. So the edge 0, 1 shows up in the list for 0. So you can see here in the list for 0 we have 1. And similarly in the list for 1 we have 0. So each edge shows up in two adjacency lists of each of the nodes that it connects. Okay. So now the obvious next question might be to create a class to represent a graph as an adjacency list in Python. Okay. This is again a question that you might get asked, or this might be part of another question that you may get asked, where you're asked to perform a breadth first search or depth first search or find the shortest path. The first step you will have to do is define a class for a graph to maintain the information about the graph as the adjacency list. Okay, so here we're creating a class graph, and the first thing we'll need inside the graph is a constructor function. So we need to put something inside the constructor function, and we know that the first argument to any graph, any class method in Python is self, which represents the object that will get created ultimately when we create an object of the class. But apart from this, what information do you need to create a graph? Now it's pretty straightforward. We can simply work with this information because these two variables together specify the graph completely. So let's simply accept num nodes and a list of edges as the information. The first thing we can do is simply store num nodes in self.num nodes, so that once we create a graph, we can access the number of nodes very easily. Then we need to create the adjacency list. So we need to create the adjacency list. We'll call it self.data. And initially we will create a list containing empty lists, and then we will fill out the empty list step by step. So what we need is something like this. In this case, because there are 5 nodes, so this is what we need to create, the 5 empty lists. Now in general, the way to create repeated elements is this. You can say, if you want to create a repeated element like this, 0 times, you type 0 times 10, and that gives you this list, 0, 0, or containing all zeros. On the other hand, if you create empty list times 10, and let's call this L1, and let's see what L1 is. It looks like you've gotten an empty list, you've gotten a list containing 10 empty lists, but let's just go into the first element. So the first element is this first empty list, and inside the first element, let us add the value 1. Okay, and then let's look at the list L1 once again, and you see what happens. This 1 gets inserted into all of these lists. Now what's the problem here? Now the problem here is that when we do this, when we create a list containing an empty list or containing any object, then the same object gets replicated 10 times, but Python does not create copies. Now when you're working with numbers, it's fine, because when you're working with, let's say, the number 0, that's fine because there's no internal structure inside 0, right? So there's nothing you can change inside the 0. It's a fixed value, fixed immutable value. So you can't really say L1 of 0 and change its value internally. What you can do is you can set L1 of 0 to another value. Let's say you can set L1 of 0 to 1. So instead of getting all zeros, you get all ones, but you cannot take the 0 and change something inside it. On the other hand, when you have an empty list here, So this is the same list that is showing up 10 different times. Each of the elements in the list, outer list, is simply a pointer to this same empty list. So what we can do is, since we can go inside this empty list and append something to it, so since this is the same object that we are seeing over and over, the one gets appended to the first list, and because the rest of them are the same object, we get back all ones inside here. Okay, so this is the reason we're spending time here is because this is a common bug that you may unintentionally execute. Whenever you want to create a list of empty lists, do not use this method. So what's the method you should use then? So here's one method you can use. Let's say you want to create a list of empty list of size 10. So you may be familiar with this object, this object called range, this function called range. What this does is, if you view it as a list, you can see that it contains all the elements from 0 to 9. Okay, now if you view the range itself, it simply shows you 0 to 10. But when you convert it into a list, you can see that internally it contains the values 0 to 9. Okay, so you can take this range and you can do something like this. Put this range, or put anything which is iterable inside these brackets, the list brackets, and then say for x in range, and simply put x. So what did that do? That did practically nothing. We simply took x from the range of 0 to 10 and returned x itself. So we created a new list like this. But suppose we multiplied it by 2 here, x by 2. So for each element in the range, we are multiplying it by 2. And so we get back a new list which is 0, 2, 4, 6, 8. So this is, each element is the double of the elements that we have in the range. Now what we need is, we need just empty lists, right? So we can simply put an empty list here and we can ignore this value x that we get here. So now we get back a whole bunch of empty lists. So let's call this L2. And what we're now doing is, for each element in the range, we are creating a new empty list. So this is important. So now when you do L2 0 dot append 1 and then check L2, you can see that 1 was only inserted inside the first list. Okay, so watch out for this. This is something that you will probably go wrong with at some point. I've gone wrong many times. And one last change we can make here is, whenever you're not using a variable in Python, it's always a good idea to just call it underscore. You can still call it x, but sometimes somebody reading your code may not understand why you have declared a variable and not used it, and assume that maybe you've made a mistake. So just to make things very clear, it's always a good idea to make something underscore. It's also a variable name, a valid name, and mark something as underscore if it is not being used. Okay. So with that whole discussion about lists, we now know how to create a list of empty lists. So here you have a list of empty lists for underscore in range num nodes. So now we have created a list of empty lists. Then for each edge in edges, we need to do something. So we need to insert it into the right lists. Okay. Now what does for edge in edges look like? So let's see, for edge in edges, print edge. Okay, each edge is a pair. We already know that. And when you have pairs or tuples here, you can get the values out. So let's call them n1 and n2, node 1 and node 2. You can get the values n1 and n2 out like this. So now we can say print n1 and print n2. You can see that we are able to get values n1 and n2 out directly within the for loop. So let's call this n1 and n2. And now this is a much more Pythonic way of writing code. So one of the things that we're also learning is how to write code which is more Pythonic, or which is idiomatic in Python. And this is again something that will impress people when you use it in an interview or a coding challenge. So for n1 and n2 in edges, what we need to do is, first we get self.data of n1. So this gives us the adjacency list for n1, the first node. And here we append the value n2. And similarly, we do the same for n2. And we append n1 to it. And that's it. Now we've set up the graph. So let's create a graph G1. Let's call this graph 1 maybe. and we simply invoke the graph function, and then we give it a number of nodes and the edges, right? So remember, self will be passed in by Python automatically as the object that is getting created. So the graph1 object essentially. So now the number of nodes is 5 and we have a list of edges. And let's see what graph1.data looks like. So there you go. You can see that 0 is connected to 1 and 4. And 1 is connected to 0, 2, 3, 4, and so on. Now, while this is okay, it would be nicer to print it like this. So maybe let's see if we can print it like this. And the way to do that is to define a wrapper function. So we define a function called __repr, and it simply takes self as the input. And what we are going to do is we are going to call enumerate on self.data. Now what does that give us? Let's just check what enumerate on self.data gives us. Well, maybe before we do that, let's see what enumerate on a list gives us. Enumerate on a list gives us this object, but let's just get a value out of it in a for loop, because you can use an enumerate in a for loop and then just print x. So what enumerate gives us is it gives us the values from the list, but apart from those values, it also gives us indices. Okay, so you can get an index I and a value v out of enumerate. So then you can see that you can print both I and v here, and you will get back the same output. Okay. So what we can say is we can do enumerate self.data. Now, because self.data contains these elements, so what we'll get back is we'll get back pairs. Let's see here. So we'll get back pairs 0, 1, 4, 1, 0, 2, 3, 4, 2, 2, 1, 3. Now this is starting to look a lot like what we want. Okay, so we'll just take enumerate self data, and we'll take these pairs. So the pairs will be a node, so node n and its neighbors. So we have the node n, so the node n will first be 0 and its neighbors will be 1 and 4. Node n will be 1 and its neighbor will be 1 and 2, and so on. And then, so for n comma neighbors in enumerate, what we'll do is we'll simply create a simple string. And here we're using string formatting. We're simply creating this string where we put this, here we place a placeholder where we put n, and then here we put a placeholder where we put neighbors. Again, let's just see what that looks like. And this is the best thing about Jupyter. While you're writing code, you can test your code right then and there simply by putting data into a new cell. So let's see graph1.data. You can see here that now we have converted that enumerated list into a list of strings. So we have a string here. This is the string 0 pointing to 1, 4. This is the string 1, this is 1 pointing to 0, 2, 3, 4, and so on. But this is still a list of strings. What we need to return from the wrapper function is a single string. So the way to join them together, whenever you have a list of strings and you want to join them together, all you need to do is you say what you want to join them with. So we want to join them with a new line, and then call the join function on that string and return that, right? So that is our wrapper function, and we'll see its uses in just a moment. And similarly, we have another function called str. Now wrapper is used when we simply type graph1. So when we type graph1, this is the output of the default wrapper function. Now this will get replaced by the wrapper function that we are defining. But when we do str of graph1, or when we do print of graph1, or when we insert graph1 into a string, that is when the str function is used. Now we will simply use the wrapper representation. So let's just put self.__repr, and that's it. Okay, so let's see now. Let's type graph1 here, and you can see that now we have this representation printed using this wrapper function that we've defined. So we have 0, 1, 4, 1, 0, 2, 3, 4, 2 connected to 1, 3, 3 connected to 1, 2, 4, and 4 connected to 0, 1, and 3. Okay, so now we have a graph data structure that we've implemented using a class, so the adjacency list, and we have a nice way to print it out. And this is just good programming practice. Now you don't have to do this in a coding competition, or you don't have to do this. It's good if you do it in an interview, if let's say you're able to type this out quickly. But when you are working on your own problems or on your own code or on a project, always make sure that any classes you define have a good string representation, so that when you type the name of a variable, you understand what it represents and you don't have to spend time thinking about it. Make it clear to yourself. Okay. So that's the adjacency list, and we'll see how that is useful in just a few moments. But here are a couple of questions for you. Try writing a function to add an edge to a graph that is represented as an adjacency list. Okay, so here we've specified all the edges right in the beginning, but can you write a function add edge which takes a couple of nodes and it inserts an edge between those two nodes? And here's a hint, this code might be useful. So do try that out. Now here's another one. Can you write a function to remove an edge from a graph which is represented as an adjacency list? So here you may have to use the list remove functions to remove a particular element from a list, but these are two good exercises to complete here. Okay. Now before we continue, let's just save our work. And we know that this notebook is running on Binder, which is a free service. So we'll just save our work by running jovian.commit. And what that will do is that will capture a snapshot of this notebook, all the changes that you've made, and put this on your Jovian profile. Now this will go on your Jovian profile, from where you can continue running it, continue executing it from where you have left off. Okay. Now another common representation for graphs is called the adjacency matrix, which is slightly different from adjacency lists. In this case, for example, the same graph here is represented using this matrix. So what we do is we create a matrix of size n by n if n is the number of nodes in the graph. And then for each node, for instance, since we have 0 and since we have an edge between 1 and 2, so if you take the first row number 1 and column number 2, you put a 1 there. Otherwise, if there's no edge, for example, there's no edge between 0 and 2, you take the 0th row and column number 2, you put a 0 there. Okay, so you put a 1 wherever there is an edge between the two nodes, and you put a 0 wherever there isn't. And you can see that there is this reflexive property here, because 1 2 is 1 and 2 1 is also 1, because these are undirected edges. Now of course, if this is a directed graph, this would be different. Okay, so an exercise for you once again is to represent a graph as an adjacency matrix in Python. Shouldn't be too hard. All you have to do is, so in adjacency list, we initialized a list of empty lists. Here you may want to initialize a list of zeros, a list containing lists of zeros. Okay. And then you may simply just want to fill in the 0 ones in the right places. Now adjacency matrices have their own benefits. Sometimes they are more useful. For example, when you want to immediately check if there is an edge between two vertices or two nodes, you can quickly look it up in the adjacency matrix. But in the adjacency list, you will have to get the list for one of them and then search through that list, which is fine for most cases, but in some cases you may just want an adjacency matrix as well. So that's one other way you can represent a graph, and that's an exercise for you. Okay, so now we know we've represented graphs, and now we can start looking at some graph algorithms, and probably the most common graph algorithm, something that you will ultimately get asked in one interview or the other if you're interviewing with a bunch of companies, is breadth first search. And breadth first search, well, this is what it looks like. So suppose you have this is a real world graph that we're looking at. So these are cities in Germany, and you can see that there are roads between these cities, and we have lengths of each road. Now we can ignore the lengths for now. What's important is that these cities are connected to each other, but not all cities are connected to all of them, all of the others. So starting from Frankfurt, you may want to find out which are the cities that you can reach from Frankfurt without stopping. So which are the cities that are one edge away from Frankfurt? And if you look at it this way, it turns out that Mannheim, Kassel, and Wolfsburg are the three cities that are one edge away from Frankfurt. Right? So if you start drawing this tree of sorts, so you will find that Mannheim, Wolfsburg, and Kassel are one edge away. Okay. Then you might ask, which are the cities which are two edges away from Frankfurt? So now the cities that are Mannheim is connected to Karlsruhe, and Wolfsburg is connected to these two cities, and then Kassel is connected to this city. Okay. So here you have these other cities. And then you might ask, which are the cities that are 3 steps away from Frankfurt? And that would be the remaining 2 cities, Augsburg and Stuttgart. Okay. Now I'll let you think about this, but what you will find in this way, as you go step by step by step, like first you're finding all the cities that are 1 step away. So all the nodes that are 1 step away from a source node. Then you're finding all the nodes that are 2 steps away from a source node. What this will give you is ultimately you will end up, for each node, you will find out how far away it is from the source. And that will be the length of the shortest path between the two. Okay. And you can verify that. I'll let you think about it. For instance, if you see, you can go to Kassel by going this way from Wolfsburg to Nuremberg to München to Kassel. But that would not be the shortest path. But binary search, this is called breadth first search. Breadth first search will always discover the shortest path, because we're first finding all the nodes at distance 1, and then we're finding all the nodes at distance 2, and then we're finding all the nodes at distance 3. And if a node at distance 3 has a shorter path, then it would have been already found when we are finding nodes of length 1 or 2 or distance 1 or 2. Okay. So that's breadth first search. So here's one problem that you might face in an interview. Implement breadth first search given a source node in a graph using Python. Okay. And here is some pseudocode. So it's always a good idea to write or explain your approach in plain English before you implement it, so that you do not make mistakes while coding. So here is the pseudocode. So if you have to write a function BFS, which takes a graph and a root or a source node. So first we say create a queue. So we're creating, and this is taken from Wikipedia. So first we create a queue. And what's a queue? Well, a queue is a very simple data structure. A queue is simply a list, and it follows a first in, first out policy. So when you have a list and you want to add something into a queue, it's also called enqueue, the enqueue operation. So when you want to add something into a queue, you add it at the end. Okay. So you have a list and then you simply keep adding things at the end. You just append things at the end of a list. But when you want to access something from a queue, you do not access any value directly. No, you always access the first available value. Okay. You access the first available value. In this case, what is called the value in front. And when you access a value, it gets removed. Okay. So in this way, you can see that it implements the first in, first out policy. Like if first we enqueue 1, and then we enqueue 3, and then we enqueue 4, and then we want to dequeue. And when we want to dequeue, we simply get the first value that was inserted, which is 1. Then maybe we enqueue a few more numbers, 5, 2, 7. Then we dequeue, and then we get back the first value that we had inserted, which is not yet dequeued. So then we get back 4 or whatever was the second value inserted initially, right? So that's a queue. And let's see how a queue is useful. So we create a queue, and then we mark the label, we mark root. We label the root node as discovered. Okay, so we need to somehow track which nodes have been discovered or visited. And first what we'll do is we will mark the root node. So let's say we're starting from the node 3. We will mark 3 as discovered. So 3 is now discovered. And as soon as we mark something as discovered, we will enqueue it. Okay. Then while the queue is not empty, which is while we have not accessed all the elements in the queue, or while we have not dequeued all the elements from the queue, we dequeue an element. So we dequeue the first element which has not yet been removed from the queue. And if we're looking for a particular goal node, then we can simply end there, like we found that node. But we are not looking for a goal node, so let's remove this code. Yeah, so we get the first element or the first node from the queue, which is not yet dequeued. And then, so for example, initially we just have 3 in the queue. So then we get back 3, we get 3 back from the queue. Then we check all the edges for 3. So we check that 3 is connected to 1 and 3 is connected to 2 and 3 is connected to 4. So we see all the edges for 3. And if the other end of the edge, we check for each node, let's say the other end of this edge is 2. We check if 2 is not yet discovered or not yet visited, then we enqueue 2 into the queue. Similarly, we check for 1. And if 1 is not yet already discovered, we enqueue 1 into the list. Similarly, for 4, we enqueue 4 into the list. Okay. So we have dequeued 3. So 3 is no longer in the queue, or we've moved forward. We're no longer going to get 3 out of the queue. But now we've enqueued 2, 1, and 4. And 2, 1, and 4, we now understand they are at distance 1. So when we pick the next element of the queue, we dequeue the next element, the first in, first out, we get back 2. And then we mark 2 as visited. Great, now we visited 2. Oh no, we mark, as soon as we are adding something to a queue, we also mark them as visited, because we've identified that 2, 1, and 4 are all at distance 1 from 3, and we've added them to a queue. So we mark them as visited. Now, when we get 2 out of the queue in the next iteration, we check if there are any nodes which 2 is connected to, those are not yet visited. So 2 is connected to 1, but 1 is already visited. So there's no need to enqueue it again. And then 2 is connected to 3, but 3 is already visited. So there's no need to enqueue it again. And so we just move forward. Then we go to 1. And when we go to 1, we realize that 0 is not yet visited. So we enqueue 0. 4 is visited. So we don't enqueue 4. Okay. And that's how we proceed. So now what you should do is you should draw this on a piece of paper and work it out. Just write on a piece of paper what would be the first element that gets inserted and what will be the elements that we will insert into the queue, etc., etc. But this is the algorithm here. Exactly what we just discovered. So we dequeue in a vertex for all the edges that start from the vertex V or the node V. If the other end of the edge is not labeled as discovered, then mark it as discovered and enqueue it into the queue. Okay, so let's implement this. Let's see if we can implement this live. So we are implementing BFS, where we will get a graph and a source node. The first thing we need to set up is a queue. So the queue is empty. Then we set up discovered, and discovered will be false initially, and it will have the length. So we want to mark it false for all the elements. Okay. And remember, now we can use this notation here because false is an immutable value. So it doesn't matter. So we don't really need to use the range or the list comprehension notation here. Then here, let's come here. So we mark the label root as discovered. So discovered of source. Let's just call it root so that we don't get confused with the terminology. So we mark discovered of root as true. Great. Then we insert, or we enqueue the root. So we type q.append. Now enqueue simply means adding something to the end, and you know how to do that in a list. You simply call q.append. So q.append root. Great. Now Python lists by default do not support a dequeue operation. So what we will do is we will set up an index which will track the first available element in the queue. Okay, so whenever we dequeue an element, we will increase the index so that we move forward. So here we have the index idx equal to 0. So now while there are elements in the queue, which means while the next available index is less than the length of the queue, first we will get the current, we will dequeue. So dequeuing simply means getting getting the first in element, the element that was most recently inserted and has not been dequeued. So we get current is q of idx, and then we can also increase idx. So as soon as we dequeue something, we update the index. So you can imagine that the index starts out here, and when we dequeue this or delete this, then we get that value out, and then we update the index to the next position. Okay, so now we have the current. So this is the dequeue operation. Then what do we have next? Now we want to check all the edges of current, right? So we are going to say for, so remember we have the adjacency list representation. So we will get for node in self.data current. So self.data current contains a list of all the nodes that are connected with the current node. So for node in self.data current, if not discovered node, so if we have not yet discovered the node, then we first mark it as discovered, and then we add it to the queue. So we do queue.append node. Okay, so what you end up with this way is, first you have the source that got added to queue, and then we inserted all the nodes which were at a distance 1 from source, and then we insert, then if you follow the trajectory, you'll see that we will insert all the nodes that are at a distance 2 from queue, and so on, right? So ultimately, when we end up with this entire process, we will have the queue, and the queue will contain the list of nodes as they would be visited in a binary, in a breadth first search. Okay, so we can simply return the queue here. So let's try it out. So we have graph 1, and let's call BFS, and graph 1 is this graph. So let's grab this image as well. So let's simply copy the code for the image and come down here. Let's come down here and put the image here. Okay, let's call BFS on graph 1, starting at the node 3. Okay, of course, this should be called graph.data. So because graph is the graph that we're working with, so we need to check graph.data here. Okay, so we start out with the node 3, and you can see that 3 first causes 1, 2, and 4 to get inserted, and then 1 causes 2 to get inserted. Okay, now that's BFS for you. It's pretty much done at this point, but what would also be helpful is maybe to keep track of what is the distance of each node, right? So we can also keep track of a distance. So let's say we have a distance which we initially set to none, which we initially set to none, and we will track a distance for each node. So we have the distance here, and initially we are going to set the distance for the root to 0, of course, because the root is at 0 distance from itself, and the distance here means the number of edges, right? Then when something is discovered, so when we are discovering a node and that node was not already previously discovered, that means that the distance for that node is 1 more than the distance for the current node which caused it to be discovered, right? So the distance for example, if you're starting with 3, the distance for 1 is 1 more than 3, which caused 1 to be discovered, and the distance for 0 is going to be 1 more than 1, which caused 0 to be discovered. So that's the distance. Great, we've now also tracked the distance. One other thing that would be nice to have is what is called the parent. If you go back here, you can see that it would be nice to know what led to Karlsruhe being discovered. Was it Mannheim, Würzburg, or Kassel? So that we can work our way backwards and find a path from Frankfurt to Karlsruhe. Okay. So for that, what we can do is we can keep track of a dictionary, of a list called parent. Once again, we will have no parents by default. So parent none. And whenever we find a node and that node was not already discovered, Then we can set the parent of that node to the current node which caused it to be discovered. Okay, and now we can return from the queue the distance and the parent. So let's see if that works. Okay, so it seems like now we have this is the order in which the nodes are being visited. So you can see that 3 is the